In 1977, humanity launched two small spacecraft into space, each the size of a small car. The Voyagers began a journey that was supposed to last only 4 years, but they continue working today more than 45 years later, sending messages from places more distant than anything made by humans has ever reached. These spacecraft have already passed by Jupiter with its storms larger than the entire Earth, by Saturn with its rings made of billions of pieces of ice, by Uranus spinning sideways like a rolling ball, and by Neptune with winds faster than sound. Now, Voyager 1 is so far away that sunlight takes more than 22 hours to reach it. That's 24 billion kilometers away. But here's what keeps scientists awake at night. The Voyagers discovered things no one expected, from active volcanoes on frozen moons to oceans hidden beneath layers of ice, and now they're detecting mysterious sounds coming from the space between the stars. What are these small spacecraft trying to tell us about what really exists beyond our solar system? Subscribe to the channel, leave your like and comment from which part of the world you're watching. Get comfortable and relax. Let's begin. Did you ever wonder how two small spacecraft built over 40 years ago ended up changing everything we know about the planets beyond Mars? That's exactly what NASA dared to attempt with the Voyager missions. Back in the year 1977, NASA launched Voyager 1 and Voyager 2 with a mission so bold it sounded almost like science fiction at the time. They wanted to visit the outer planets of our solar system and send back up-close and personal data and photos, something nobody had ever done before. At the time, missions were challenging and risky, with a high chance that something could go wrong. These spacecraft were powered by technology from the 1970s, with the computing power far less than a modern calculator. Yet the hopes placed upon them were monumental. People at NASA carefully planned their launch windows, their destination, and their hardware, but few imagined just how far and how long Voyager 1 and Voyager 2 would travel, or how many secrets they would uncover. The very idea for the Voyager mission was sparked by a rare planetary alignment that would only happen once every 176 years. This alignment, which was set to occur in the late 1970s and early 1980s, meant that the major outer planets, Jupiter, Saturn, Uranus, and Neptune, would be lined up in such a way that a spacecraft could visit all four in succession using something called gravity assist or slingshot maneuvers. In simple terms, the spacecraft would use the massive gravity fields of these planets to get a tremendous speed boost, flinging them from one planet to another to the next without using huge amounts of fuel. This was a game changer because otherwise the distance and fuel requirements would have made a 4-planet tour impossible. NASA saw a unique, virtually unrepeatable opportunity to explore 4 unfamiliar worlds using 2 unmanned probes. These probes, if everything went right, would blow open the doors of discovery for entire generations. The early goals for the Voyager missions actually sound fairly simple when you hear them today, but back then they were revolutionary. The basic plan was to send Voyager 1 and Voyager 2 to Jupiter and Saturn. Each would give us our first detailed close-ups of the planets, their rings, and their moons. Nobody had seen the surfaces of these moons in detail, or even knew what many of them looked like close up, or what lay inside those colorful gaseous storms swirling on the planets. The first mission objectives included studying not just the atmosphere, but also the complex magnetic environments, or magnetospheres, surrounding each planet, their many rings, and whatever moons they encountered along the way. There was also a strong desire to take the best possible photographs and gather scientific data that simply wasn't possible using telescopes from Earth. The possibility of discovering something unexpected was almost a guarantee and made every step a source of mystery and excitement. But forget for a second about all the technical planning and just think about the odds these spacecraft faced. The chances of flawless launches, multiple flybys with razor-sharp timing, and critical course changes, all of this depended on everything working perfectly with technology that, by modern standards, would be considered ancient. Voyager 1 was launched first on the 5th of September 1977, followed by Voyager 2, which, despite its name, set off a little earlier on the 20th of August 1977. Each weighed about 822 kilograms at launch and carried more than a dozen scientific instruments, as well as cameras, antennae, and even a record known as the Golden Record, packed with sounds and images from Earth just in case the probes ever encountered intelligent life outside our planet. The amount of planning and foresight involved was enormous, but even so, the mission was slated to last only about 4 years, long enough to get to Saturn and Jupiter, collect data, and then likely go silent. From the moment they left Earth's atmosphere, the Voyager probes navigated the vast, unforgiving expanse of space with the help of mission controllers who performed countless calculations and mid-course adjustments to make sure the probes would arrive at precisely the right path for each planetary encounter. The timing had to be just right so the spacecraft could use the slingshot effect from Jupiter to head safely toward Saturn and, for Voyager 2, onward toward Uranus and Neptune. Gravity assists were a relatively new technique at the time, but they made the difference between a quick detour and an extended grand tour. Every opportunity for improvement and correction had to be seized. Small course changes just days or hours before planetary flybys spelled the difference between dramatic success and missing a moon by thousands of kilometers. The nervous excitement in those NASA control rooms was almost unbearable anytime they made a correction or sent new commands out to the probes. As the years went by, these temporary spacecraft kept working and continued to astonish everyone. After reaching Saturn, Voyager 1 was launched off the plane of the solar system to eventually begin its journey toward the frontier of interstellar space, while Voyager 2 took a different path, aiming for the two ice giants, Uranus and Neptune. This wasn't just luck or chance. It was smart thinking and backup planning. NASA built redundancy into the mission from the beginning, with both probes able to perform many of the same scientific tasks and each taking its own route to maximize the information NASA could get for each planet. When original plans called for shutting down the spacecraft after Saturn, the reality didn't match those modest expectations. Both Voyagers were still healthy, transmitting valuable data back to Earth. NASA kept extending the mission, first for Uranus and Neptune, then for a long-term interstellar voyage that nobody seriously considered possible at the time of launch. One of the most ambitious and fascinating elements of the Voyager mission was not just where these spacecraft were going, but how they would last so long. Their power came from 3 radioisotope thermoelectric generators, basically small nuclear batteries that converted heat from decaying plutonium into electricity. This system meant that, instead of relying on solar panels, which are useless that far from the sun, the Voyagers could keep running their cameras and instruments even in almost total darkness. Cooling systems, heaters, and backup electronics brought the total number of major systems into the dozens, all working together to keep the spacecraft alive. But over time, power would fade and instruments would need to be shut down one by one. NASA mission planners knew they would have to make choices, sometimes retiring instruments gracefully, sometimes figuring out creative tricks to keep vital equipment running just a little bit longer. That pioneering engineering also came with real risks. Tiny mistakes could mean disaster. The spacecraft might veer off course, miss a planet, or simply be out of contact with Earth forever. To cope, NASA's team baked redundancy into every layer of the mission, from duplicating many instruments to writing flexible, reprogrammable software, an innovation that bought the spacecraft extra years of life. Some of the onboard memory was wiped and reprogrammed from Earth, sometimes taking hours just to confirm that the new instructions had been received, since even radio signals took hours to travel millions or billions of kilometers in space. The controllers faced situations nobody had truly prepared for. Frozen hydrazine fuel lines, jamming tape recorders, and malfunctions in steering thrusters. More often than not, the team found fixes, each one keeping the mission alive just a bit longer, and each time wringing new value out of the already extraordinary investment. From the first flyby of Jupiter, it was clear the scope of scientific discovery was going to surpass anyone's wildest predictions. The probes returned breathtaking images of swirling storms the size of Earth, volcanoes erupting on distant moons, and rings around planets that had never been detected from terrestrial telescopes. Over the years, the mission's goals expanded and adapted, stretching further than originally planned. The scientific rewards grew with every kilometer traveled and every planet explored, accumulating a treasure trove of data that has remained valuable for decades. With so many planetary systems to visit and more than 60 previously unseen moons to examine, Voyager quickly became humanity's eyes and ears to a universe of phenomena that nobody could have guessed at before 1977. Another remarkable aspect of the Voyager mission was what it meant for space science as a field. It inspired future missions and fostered international collaboration, making deep space exploration more of a cooperative endeavor. Its success showed that carefully designed missions using tested hardware could go far beyond their initial mandates if handled well, and that sending robots across the solar system was not just possible, but hugely rewarding. Even now, decades after launch, the Voyager mission remains a gold standard for careful design, mission planning, and the ability to react nimbly to challenges along the way. NASA learned lessons about redundancy, backup systems, communication delays, and how to problem solve on the fly that would set the blueprint for missions like Galileo, Cassini, New Horizons, and future probes heading even farther out into space. The cultural impact was also enormous. The Golden Record, a time capsule of voices, sounds, and images, made the mission famous well beyond the world of scientists and engineers. People everywhere could imagine the spacecraft drifting through the void, carrying an introduction to Earth for whoever or whatever might find it millions of years in the future. Voyager's travels were covered by newspapers, television, and radio. Even today, the images and records from Voyager regularly resurface and fascinate new generations. Its impact reached not just scientists, but schoolchildren, artists, writers, and dreamers. It helped spark a new sense of curiosity about the universe and our place in it, especially as the Voyagers continue to transmit weak but steady signals from farther away than any human-made object has ever traveled before. Looking back, it's amazing that what started out as a 4-year project to fly by 2 planets in the outer solar system turned into one of the longest, most productive scientific missions in history. Both Voyager 1 and Voyager 2 keep sending valuable data from the frontiers of the Sun's domain and out into the great unknown between the stars. Despite being launched with the technology of the late 1970s, they have weathered harsh radiation, cosmic rays, micrometeoroids, and the ravages of time and distance. They've become the elder statesmen of NASA's fleet, living proof that with clever planning and just a bit of luck, a small piece of humanity can leave Earth and keep sharing discoveries long after anyone expected. Their continuing survival is both an engineering triumph and a scientific goldmine, with impacts and lessons that don't seem likely to end soon. Even as the next generation of missions prepares to build on these successes, there's no denying the magic of Voyager's humble beginnings. The launches of Voyager 1 and Voyager 2 marked a pivot point in the story of human curiosity and exploration. They are reminders of what can be accomplished with bold vision, clever science, steady nerves, and maybe a little bit of daring. The legacy of the Voyager mission will echo for centuries to come, continuing to inspire those who one day may find themselves looking up at the sky and wondering just where Voyager is right now, and just how much more is waiting to be discovered out there among the stars. Just after gaining momentum from their successful launches, both Voyager 1 and Voyager 2 found themselves heading straight for one of the biggest milestones in space exploration, Jupiter. Even though everyone had seen Jupiter through telescopes for centuries, nothing prepared researchers for what Voyager would uncover up close. As the spacecraft approached, the sense of anticipation shot up in NASA's control rooms. What kind of weather did Jupiter really have? Were the swirling spots and bands just colorful patterns, or were they signs of wild, active processes that could teach us more about gas giants everywhere? In the late 1970s, as Voyager's cameras started to snap high-resolution photos from closer than anyone had ever managed, surprises began coming in almost immediately. One of the first things everyone noticed was the raw energy of Jupiter's weather systems. With closer views, Voyager's cameras sent back sharp, detailed images of massive storm systems, including that famous Great Red Spot, a gigantic hurricane winding in Jupiter's atmosphere. For the first time, scientists got to see the fine details inside the storm. Smaller, rotating storms within the larger one, knotty clouds and fast-moving jet streams. The scale was hard to process. That storm alone was found to be larger than all of planet Earth, and evidence suggested it had been spinning for at least 3 centuries, maybe longer. The data showed that Jupiter wasn't just a pretty face in the solar system. It was home to a kind of atmospheric chaos, with winds blasting through its cloud tops at hundreds of kilometers per hour, creating belts and swirling patterns as far as the eye could see. As Voyager's flybys continued, scientists back on Earth watched the wild display of colors, lightning, and turbulence in Jupiter's clouds. They saw oval-shaped storms popping up, some merging, others splitting apart, behaving like a weather laboratory in fast forward. Instead of a calm planet, Jupiter turned out to be a roaring, ever-changing world. Voyager's cameras caught smooth streaks, rough-edged clouds, and white thunderstorms crackling just below the colorful tops. Using specialized filters, the spacecraft even made out layers in Jupiter's clouds, showing there were ammonia and sulfur clouds moving around and colliding deep in the planet's thick atmosphere. For the first time, researchers started to understand that the look of Jupiter from telescopes told only a small part of the story. The spacecraft had peeled back the curtain on an alien world's weather in a way nobody expected. Jupiter's environment proved much more dangerous and surprising than anyone thought before Voyager arrived. Not only were the storms immense, but Voyager's sensors also picked up levels of radiation that could have fried the electronics of less protected hardware. Jupiter has vast belts of charged particles whizzing around its magnetic field. These belts are so intense they form the strongest radiation environment anywhere in the solar system, aside from the Sun. The data forced researchers to rethink how planetary magnetic fields work and what space might be like around other gas giants elsewhere in the galaxy. Jupiter's magnetic field stretched far out into space, over several million kilometers, and created an invisible, deadly zone that affected its moons, its thin ring system, and even the solar wind blowing from the Sun. The readings Voyager sent back became a must-have reference for any future missions that would come near Jupiter or its moons, helping design better protected spacecraft. What might have shocked scientists most was what Voyager found as it passed by Jupiter's moons, especially Io. Before Voyager, people expected to see rocky, cratered worlds, maybe with a little ice here and there. But when the first images from Io started coming in, they showed a surface unlike any other, painted in vibrant yellows, reds, and white patches, with odd-looking features that looked almost like lakes or strange blisters. Then, geological data started to spill in. There were signs of volcanoes. There were shapes that looked like fresh lava flows, but nobody on Earth had ever imagined active volcanoes on a moon so far from the sun. Then, on the 28th of March, in the year 1979, the raw evidence arrived. Pictures of an eruption were clearly captured. Dust, gas, and sulfur rising up and out, spraying high above the surface. It quickly became clear that Io was the most volcanically active world in the solar system, way beyond anything on Earth. Io's volcanoes were erupting with such power because of Jupiter's immense gravity tugging and flexing the little moon as it orbited, warming up its insides. This was a kind of heating process nobody thought could exist on such a scale, and it not only explained the constant eruptions, but also meant Io had a surface that was always changing. No ancient craters, no static spots, just a landscape getting wiped clean and remade all the time. The volcanic eruptions sent massive plumes of material far into space, adding a whole new chemistry to Jupiter's magnetic environment. And Voyager showed these volcanic plumes so well that to this day the images are still used in textbooks. The discovery of Io's activity completely changed how people thought about moons and what might be possible elsewhere, even in the far reaches of the solar system. The surprises didn't stop with Io. As Voyager flew past some of Jupiter's other major moons, Europa, Ganymede, and Callisto, it gathered images and data that were almost as stunning. Europa, in particular, showed a smooth, bright surface with streaky lines and very few craters, hinting at another possible geologic oddity, a global icy shell, maybe even with an ocean underneath. Ganymede turned out to be the largest moon in the solar system, bigger than Mercury, with bands and grooves crossing its icy face. Callisto, the fourth largest moon, showed a heavily cratered ancient surface, a record of billions of years of cosmic collisions. Each moon was a world of its own, and Voyager's flybys gave scientists the first real clues that the satellite systems around giant planets could be almost as complex and interesting as the planets themselves. Voyager didn't just study storms or moons, it also found features around Jupiter nobody knew existed. For a long time, astronomers on Earth searched for rings around Jupiter but found nothing. That changed thanks to Voyager's sensitive cameras and perfect positioning. In early images, a faint, dusty ring showed up, circling Jupiter in a thin band. It wasn't obvious from Earth, but once spotted, it explained a lot of little mysteries about how Jupiter's moons and magnetic field interacted. Later missions would confirm the ring's presence, but it was Voyager that discovered it first, showing that Saturn wasn't the only planet in the solar system with a ring system, and raising new questions about how rings form and how long they can last. The immense scale and complexity of Jupiter's radiation belts, rings, storms, and moons pushed researchers to update their models. Previous theories needed revisiting. Everything from weather cycles to magnetic fields to how moons interact with their parent planets entered a new phase of research after Voyager passed by. Some of the instrument readings showed patterns and environmental challenges no one had ever recorded. It was now clear to space agencies that any future robotic or crewed mission to that part of the solar system would have to be ruggedized to withstand the radiation and wild magnetic field swings measured by Voyager. At the time, this guided urgent upgrades in planned hardware for later missions like Galileo. Voyager's data also showed Jupiter's environment wasn't isolated. Particles escaping from Io's volcanoes became trapped by Jupiter's magnetic field, forming a donut-shaped belt of charged particles known as a plasma torus that wrapped right around the planet. This strange effect completely changed the way scientists thought about interactions in planetary systems. For the first time, It looked like small bodies could actively alter a huge planet's environment, shaping not only their own orbits, but the entire space around a giant world. The evidence that Io's eruptions could fuel Jupiter's immense auroras, the planet's own versions of northern and southern lights, meant that moons weren't just passive rocks, they were active players in building a planet's space weather. This link between volcanoes, plasma, and glowing auroras was a brand new idea, and it came straight from Voyager's data. There was more than just hardcore science at stake when those first close-up images from Voyager arrived. The images transformed public curiosity into real fascination. For the first time, ordinary people could look at color photos of towering Jovian storms, detailed shots of volcanic explosions on a moon, and pale rings circling a planet over 500 million kilometers away. The raw visual record brought home just how much was happening in space that nobody had ever guessed at before. News reports, science classrooms, and magazines everywhere picked up Voyager's Jupiter images and discoveries, making them a cultural reference. Even people with no scientific background could appreciate the magnitude of observing a volcanic eruption in action out among the moons of Jupiter. By looking more closely at the data, teams from all over the world found puzzling small-scale events on Jupiter and its moons. Some storms seemed to pop up overnight, lasting just a few Earth days. Others spiraled outward for decades. The variations in color, shape, and speed inside Jupiter's cloud bands told scientists about chemistry, temperature, and wind patterns at different depths in the atmosphere. No one had built weather models complex enough to cover this kind of behavior before. Each set of new images and measurements forced experts to think again, to invent new ways to track heat, energy, and water vapor deep below Jupiter's visible cloud tops. The newly detected ring around Jupiter, very thin and made mostly of tiny dust grains, opened the door to studying how such ring systems form and vanish. Voyager helped scientists realize that rings might not just belong to Saturn. They could be a common part of planetary systems, made by small moons getting hit by meteorites or by material escaping from moons and spreading out over time. The ring influenced how Jupiter's magnetic field worked and how radiation belts were structured, becoming another part of the puzzle for understanding local space weather. This new realization changed how researchers looked at giant planets everywhere, from Saturn and Uranus in our solar system to the big exoplanets now being discovered around other stars. Another key thing Voyager taught everyone was how dynamic and unpredictable these outer planetary environments could be. Features like auroras that flickered and changed day by day, spotty storms, and sudden upwellings of clouds showed that Jupiter wasn't a static planet by any means. Every glance revealed motion, change, and transformation. The spacecraft traveled through the footprint of lightning bolts that would dwarf anything on Earth, registered how the planet's massive magnetosphere wobbled and shifted, and even recorded mysterious little flashes and glows in Jupiter's upper atmosphere. Each one of these measurements brought back more questions and new research projects for the following years. It's important to remember how limited knowledge was before Voyager got there. When telescopes on Earth looked at Jupiter, some of the storms, like the Great Red Spot, had been charted for decades, even centuries, but nobody really knew how deep they went or what kept them swirling endlessly. Voyager allowed scientists to estimate rotation speeds inside Jupiter and guess at how much heat was rising up through its clouds, answering basic questions like how much sunlight reached different layers or what actually kept those giant storms spinning so long. The storm images and weather records collected by Voyager formed the backbone of what is now a thriving field of planetary meteorology, a science that barely existed before those flybys. The public, too, got caught up in all the discoveries. Magazines and newspapers in the late 1970s printed color images of volcanoes erupting on Io, showing a moon that looked nothing like the cold, dead craters seen elsewhere. School kids learned new facts about planetary rings for the first time, seeing that Saturn isn't alone with its dazzling jewelry. The excitement reached adults working in totally unrelated fields. They saw something happening out in space so vast and strange that it changed the way everyone imagines our solar system. The conversation sparked by Voyager's Jupiter photos spread well beyond science conventions and became a regular topic in coffee shops, classrooms, and living rooms all over the world. Looking at how the mission's discoveries reshaped science, it's clear that Voyager's time near Jupiter built the foundation for everything that came after. Later spacecraft like Galileo in the 1990s, Juno in the 2010, and multiple theoretical missions proposed for the future all used Voyager's Jupiter data as a starting point. The images and measurements taught scientists about priorities, what instruments to build, which areas to fly by for the best science, even how to protect electronics from furious radiation. The presence of volcanic activity on a moon, unknown weather types, and faint, previously invisible rings all made future mission teams work harder and think bigger. Even now, when a new generation of scientists and engineers plans a giant planet mission, Voyager's trove of Jupiter data is one of the first resources they check. In practical terms, the lessons learned about Jupiter's environment transformed the risks of later missions. Now, space agencies knew about the punishing radiation, the plasma belts, and the need to pay attention to where a spacecraft flies. They could make smarter, tougher probes. Galileo, Juno, and all robotic vehicles flying out that way were built to handle these challenges. With each improvement, the hope is to unlock even more of Jupiter's secrets, building directly on what Voyager saw first. When it comes to what the discoveries at Jupiter did for the idea of planetary systems, Voyager completely changed expectations. It wasn't just that there was a giant planet with storms and moons, it was that those moons were active, the weather was volatile on a scale researchers hadn't dreamed of, and the subtle rings and radiation belts tied everything together into a package more complex than anyone had planned for. With the freshest, closest looks ever at a whole family of moons and atmospheric features, Voyager made sure the next generation of questions was even bigger than the last. That mix of groundbreaking science, public excitement, and unexpected complexity made both Voyager 1 and Voyager 2's journey by Jupiter a landmark in space exploration. The secrets pulled out of the swirling clouds, explosive volcanoes, and faint rings added chapter after chapter to the story of what the solar system really looks like up close. Even decades down the line, many of the discoveries made around Jupiter are still a regular topic of study and a springboard toward new theories. And the wild, living, brightly colored world that Voyager revealed remains one of the solar system's most unforgettable destinations. After shaking up everything we thought we knew about Jupiter, it was only natural for expectations to be sky high as the Voyager spacecraft approached Saturn. By the early 1980s, Voyager 1 and Voyager 2 were on their way for flybys that would change how we look at this ringed planet forever. No one disputed that Saturn, even from Earth, looks beautiful through a telescope, but the reality turned out to be so much richer and stranger up close. The spacecraft started sending back images that literally had scientists gathered around monitors in the middle of the night, because Saturn's rings, moons, and swirling globe looked nothing like the smooth, simple view we'd gotten from afar. Each photo, each measurement pulled the curtain back on details that had stayed hidden for centuries, and suddenly, Saturn wasn't just a pretty stripe in the sky. It was a world teeming with complexity. First, there's no way to talk about Saturn without focusing on its rings. Even in the earliest days of astronomy, those rings grabbed attention. Yet nobody truly grasped their full nature until Voyager sailed past and photographed them from just a few 100,000 kilometers away. The images revealed a structure far more complicated than a set of neat, flat hoops. Voyager's equipment showed thousands of fine, crisp ringlets within the major rings, separated by gaps, some as wide as cities on Earth, others as narrow as a highway. Before this, the division that was best known was the wide Cassini division, a dark gap clearly visible from decent-sized Earth telescopes. With Voyager's high-contrast photographs, it became clear that Saturn's rings are actually a busy traffic jam of ice and dust, ranging in size from grains like sand all the way up to mountain-sized boulders, all orbiting Saturn at different speeds depending on how far they are from the planet. Some of the most surprising discoveries involved the patterns inside the rings. For instance, Voyager found ghostly spokes stretching across the rings. These were temporary bright bars that would appear, fade, and move within hours. At the time, scientists didn't have a solid explanation, but later work suggested they could be caused by charged dust particles floating above the ring plane, influenced by Saturn's powerful magnetic field as it sweeps past. Voyager images also showed waves and ripples inside the rings, like the tracks left by a boat in water. These disturbances hinted that some moons of Saturn, or even invisible moonlets, were moving through the rings and using their gravity to sculpt the icy particles, carving out distinct features and gaps as they passed by. It turned out Saturn's rings were anything but static. They were busy, changing, and full of motion. Of course, the rings weren't the only game in town. Saturn itself turned out to be fascinating and a little weird. More than just a gas giant covered in yellow and gold bands, Voyager's close views showed a world with hexagonal wind patterns at its poles and unusual spots that would appear and disappear from one flyby to the next. Its upper atmosphere, with bands running parallel to the equator, contains storms, both large and small. Voyager measured wind speeds at over 1,100 kilometers per hour, much faster than hurricanes on Earth. By looking at the sunlight passing through Saturn's atmosphere, Voyager instruments also found out that its upper layers are mostly hydrogen and helium, with trace amounts giving the planet its pale gold color. Studies of temperature, cloud altitudes, and composition provided fresh insights into how Saturn moves heat around and why its clouds look so smooth from Earth but show so much structure up close. The second key area where Voyager pushed the limits was Saturn's moons. Titan had always intrigued astronomers. It's bigger than the closest-in planet Mercury and was known since the 1940s to have a thick atmosphere, but nobody could see through the orange haze with any clarity. Voyager's passage past Titan was a real highlight. Its cameras couldn't quite see through the thick orange clouds using only visible wavelengths, but special instruments on board measured how sunlight and radio signals passed through Titan's air. They found a dense, nitrogen-rich atmosphere, almost like a thicker version of ancient Earth. Underneath all that haze, Voyager couldn't spot any continents or oceans, but the chemistry was there. Hydrocarbons like methane and ethane, and clouds that hinted at exotic chemical cycles happening far away from the sun. The data set off a wave of new ideas about whether such an environment could be hospitable to life, or at least prebiotic chemistry, and made Titan a prime target for future landers and probes. Saturn's collection of other moons also presented plenty of curveballs. Enceladus, one of the brightest objects in the solar system, appeared almost too clean, as though something was constantly resurfacing or renewing its outer layer. Voyager glimpsed hints of smooth plains and crater-filled areas, suggesting geologic activity. The small moon Mimas showed an enormous impact crater, so massive it looked like the moon could have split in half. Rhea, Dione, Tethys, and others each had their own unique characteristics. But a recurring surprise was that many of these icy satellites weren't just battered rocks. They showed evidence of tectonic features, cracks and ridges, as well as smooth surfaces that suggested chemical reactions or maybe even internal heat. It's worth noting that, at the time, nobody seriously imagined ice worlds might be geologically active. Yet Voyager's data pointed exactly in that direction. Another strange feature Voyager exposed was the so-called shepherd moons. Scientists had theorized these could exist, but Voyager's camera system spotted small moons nestled up close to the F-ring and other thin ringlets. The role of these moons is to herd or corral ring particles, using gravity to keep the rings skinny and well-defined instead of spreading out into a flat pancake. These shepherd moons periodically steal or scatter small bits of material, helping to shape ring edges and create sharply defined boundaries. This was clear proof that the structure of planetary rings isn't just a question of where material happens to fall, it's an ongoing dance between gravity, moon orbits, and ring particles, with each little moon acting almost like a traffic warden. This kind of moon-ring interaction turned out to be a repeated theme in planetary science, shaping not just Saturn's rings but ring systems all across the solar system. Saturn's magnetic environment brought even more surprises for the mission science teams. Saturn has a strong magnetic field, but it doesn't quite work like Jupiter's or Earth's. Voyager's magnetometers measured not just the field itself, but the way Saturn's magnetic poles seemed closely aligned with the planet's rotation axis, something no one had expected since Earth's poles are offset. Voyager also picked up on intense radio emissions, ones that change with time as Saturn spins and as solar conditions vary. These radio signals help scientists map out storms in the magnetic field and reveal details about the flow of charged particles trapped within it. In the years after the Voyager flybys, combining data from these magnetometers with later missions led to significant advances in understanding space weather around giant planets. Voyager didn't just open Saturn's secrets to science, it opened them to public imagination, too. The photographs of Saturn's rings against the planet's disk, the first close looks at moons like Enceladus and Mimas, and images of the hexagon-shaped jet stream spinning around Saturn's North Pole all became instantly iconic. Suddenly, Saturn was more than just a pretty image on a telescope slide. Its rings had texture and drama. Its moons held mysteries worth revisiting. Children in classrooms saw glossy photos of distant landscapes that looked like they belonged in another solar system altogether. Science writers and artists used Saturn's new details everywhere, turning Voyager's hard data into something millions could see and connect with. The mission also made a real impact on the way scientists think about the origins and evolution of planetary systems. For example, by evaluating the condition of Saturn's tiny ring moons, Voyager helped confirm that the rings might be much younger than Saturn itself, maybe only 100 million years old, not as ancient as the planet. The dust, ice, and moonlets circling Saturn could have come from destroyed moons or comets smashed to bits by gravity, a process that might still be happening even now. The intricate balance between material falling toward Saturn, being swept up in rings, and ejected by moon gravity is a window into what might happen around other worlds with rings, whether inside or outside our solar system. Voyager also contributed a lot to our understanding of chemistry in cold places. Saturn's cloud-top temperatures average about -180 degrees Celsius. Its upper clouds are ammonia ice, but Voyager found more complex hydrocarbon haze at higher altitudes, giving the planet its distinct golden hue. Scientists tracked the sunlight reflected and absorbed across ultraviolet, visible, and infrared wavelengths, figuring out the thickness and height of clouds. patterns found in these temperature maps helped researchers model the movement of heat from the planet's interior to its surface, an important clue to how Saturn and planets like it shine with more energy than they receive from the Sun. There were opportunities for scientists to track changes over weeks and months as the two Voyager spacecraft made their sequential passes. They caught views of storms evolving. Occasionally, features that showed up in one set of photos looked different in the next, helping build a timeline for Saturn's atmospheric changes. Some ring features also shifted, hinting that Saturn isn't a static world, but one that's constantly evolving. The precision of Voyager's measurements, taken from millions and millions of kilometers away, meant researchers could make the first serious maps of how time, sunlight, rotation, and gravity all interact out near the solar system's edge. If you ask researchers what really shifted the paradigm with Saturn, most will point to the fact that Voyager made clear the absolute diversity of what we call moons and how much they can influence the main planet. Some are ice balls with maybe hidden oceans, others are battered rocks. Some have orbits so close together they actually swap places over thousands of years. The sharp lines, smooth patches, and totally unexpected grooves seen on moons like Tethys and Dione created a rush to come up with new theories. These weren't sidekicks to Saturn, they were worlds in their own right. Titan's thick haze, measured directly by Voyager's instruments, automatically made it a focus for astrobiological curiosity. For all the hard science, one of the strongest outcomes was this renewed appreciation for worlds that might hold ingredients for life, even if they're wrapped in ice or buried beneath an orange fog. The spacecraft's inability to see the surface only heightened the sense of urgency, decades later, that led directly to a new generation of missions with radar and landers sent to Titan's hidden shores. Voyager data still forms the backbone of how future scientists and mission planners think about Saturn and its vicinity. For mission designers in the 1990s and beyond, preparing projects like the Cassini orbiter, every tiny ringlet, faint moon, radio wave, and atmospheric measurement from Voyager counted as essential background information. Cassini, when it arrived decades later, confirmed and expanded almost every one of Voyager's great finds and built on that foundation by dropping a probe right onto Titan's surface. Looking at the bigger picture, Voyager showed that studying Saturn wouldn't just answer questions about the planet and its surroundings, it would open up many new ones too. For example, the magnetic field data fed straight into how space weather works at planets that have very rapid spins and mostly hydrogen-helium atmospheres. The shifting, evolving features in the rings inspired lines of research about similar disks and bands seen around young stars far from our solar system. The way that shepherd moons controlled ring edges changed models of planetary formation everywhere. Voyager's legacy became a puzzle work that scientists keep piecing together with every new mission and discovery. On the technical side, the Voyager encounters at Saturn forced a reality check for how much punishment electronics, power systems, and instruments can handle on long, cold journeys. Saturn is almost 1.5 billion kilometers from the Sun, and the feeble sunlight reaching the region means that thermal management and radiation toughness have to be prioritized. Some Voyager instruments worked close to their technical limits, and their successes and failures gave planners crucial experience for engineering upgrades in later missions. Every lesson from how cameras handled low-light photos of the rings to data downlink schedules across gigantic distances shaped how we operate robot explorers in the most distant reaches of the solar system. In the decades since, evidence from Voyager's Saturn flybys has been checked, expanded, and sometimes challenged by telescopic observations and more modern probes, but those original images and measurements from the 1980s still sit at the core of planetary exploration. They're reference points, the base data against which all new findings are compared. From the structure of Saturn's rings to the odd beauty of Titan's haze, from the hexagonal jet stream spinning at the North Pole to the fresh craters on little moons, Voyager's findings set the stage not just for Saturn, but for how we explore planetary systems altogether. So when you look at anything else we've learned about our solar system, it's clear that a huge part of our confidence, our curiosity, and our questions are rooted in the work done as Voyager sailed past Saturn. Without that avalanche of discoveries, from ice volcano hints to the shepherd moons to the golden clouds drifting over the ringed world, much of what we now take for granted about planets, rings, and dynamic, evolving moons would have never come to light. Saturn's true complexity and beauty didn't just surprise planetary scientists, they shifted the whole conversation about what's possible on worlds that seem so different from our own. Voyager's historic flybys opened the doors for deeper, richer science, with every new mission standing on the foundation laid in those days as two little spacecraft sent home our first real roadmap of the Saturnian system. As discoveries around Saturn pushed the boundaries of what spacecraft could reveal, Voyager 2 set its course for even more uncharted territory. The next stop, Uranus, a planet that had mostly been a fuzzy blue-green dot in even the best telescopes back on Earth. What nobody realized at the time was just how many surprises would be packed into that distant world, starting with the way Uranus spins. When Voyager 2 flew by Uranus in January of 1986, it became the first and only spacecraft to get a close look at this ice giant, instantly upgrading everything scientists thought they knew about it. One of the most striking things that Voyager 2 showed everyone about Uranus is just how dramatically tilted it is. Unlike any other planet in our solar system, Uranus pretty much rolls around the Sun on its side, tipped over at about 98 degrees. This means that for decades at a time, one pole is pointed more or less straight at the Sun, while the other is plunged into darkness. Researchers didn't fully appreciate how odd this made Uranus until they could see up-close Voyager images and take fresh measurements. Instead of parallel bands running neatly east-west like you'd see on Jupiter or Saturn, Uranus has a much more muted stripe pattern and wildly different seasonal effects. Thanks to Voyager's instruments, scientists collected the first up-close weather data for a world where sunlight falls at such an extreme angle, and it changed how everyone thought about planetary seasons. Before Voyager arrived, there were people who thought maybe Uranus would be a simple, bland world. Cold, dark, probably sporting some faint rings and not much more. But as Voyager 2 made its closest approach, within about 81,000 kilometers of the cloud tops just after sunrise on January 24, 1986, it started to spot subtle but real cloud patterns and bright spots in the blue-green haze. The blue-green color comes from methane gas floating high in the atmosphere, which absorbs red light and reflects back blue and green tones. Far from being still and boring, Voyager measurements showed active weather, storms, winds that raced along the equator at nearly 900 kilometers per hour, and faint but real changes from one day to another. What seemed like a plain ball of gas was actually hosting dynamic processes, with weather systems that are still not fully understood decades later. It wasn't just the weather that surprised people. Uranus's system of rings was known before the flyby, but Voyager 2's high-resolution cameras spotted several more thin, dark rings that had been missed by telescopes on Earth. The main rings are not as dramatic or bright as Saturn's, but they're still remarkably well-defined and tightly packed. Using onboard instruments, scientists figured out that these rings are made mostly of dark, rocky material, not ice like Saturn's rings. Voyager found 11 distinct rings, each with specific widths, gaps, and shapes carved out by gravity and collisions over millions of years. The existence and stability of such narrow, clean-cut rings led specialists to ask how such structures had stayed around for so long and how small moons might be shaping them. Voyager 2's flyby didn't stop with Uranus itself. It also documented a whole family of new moons, expanding Uranus's known satellite count by 10 at a stroke. Some moons had orbits that suggested they might be guiding the rings or even causing the mysterious shapes and gaps within them, what later became known as the Shepherd Moon effect. Each moon brought its own surprise. Miranda, for example, provided one of the most jaw-dropping moments of the Uranus encounter. The images beamed back showed an icy landscape full of deep canyons, steep cliffs, and jumbled patterns that looked almost like pieces from different puzzles stuck together. There were grooves and ridges taller than the Grand Canyon on Earth, plus what seemed to be evidence of upwelling from inside Miranda at some point in its past. These features showed not only that the moon had been intensely geologically active, but that it might have practically shattered and reassembled itself in the chaos of its ancient history. The variety of Uranian moons didn't stop with Miranda. Ariel and Umbriel, also observed up close, displayed a contrast in brightness and surface markings. Ariel looked comparatively bright and smooth, hinting at periods where its surface may have been renewed by ice flows or internal heating, similar to what was a surprise at Saturn's icy moons. Umbriel, on the other hand, appeared much darker, with large impact features and an ancient, rugged appearance. Voyager's snapshots of these moons' surfaces were the clearest anyone had ever seen, and, together with orbital data, they changed thinking once again on how ice, rock, and even internal oceans might move and interact well outside the best-known part of the solar system. Some of the real scientific excitement came from Voyager's deep dive into Uranus's magnetic field. This turned out to be even stranger than what was found at Jupiter or Saturn. The spacecraft discovered Uranus's magnetic field is not centered in the planet, and it doesn't line up with the tipsy planet's spin axis. Instead, the field was seriously off-kilter, tilted more than 59 degrees away from the rotational axis and shifted up from the planetary center. This means that as Uranus spins, its magnetic field sweeps around in a lopsided corkscrew fashion, creating a wildly variable magnetosphere, the area around a planet controlled by its magnetic field. Scientists realized this meant Uranus probably had a magnetic core much closer to the surface, and that the icy, slushy layer between the inner core and the upper atmosphere might be stirring up the field in complex ways. Mysterious changes in charged particles and space weather around Uranus could now be tracked, pointing toward a richness of planetary physics not previously expected for a quiet ice giant. Another point that stood out from Voyager's time at Uranus was the planet's overall energy and heat budget. Unlike Jupiter and Saturn, Uranus seemed to be the oddball when it came to radiating heat. It does not give off much more heat than what it receives from the Sun. This finding, measured with Voyager's infrared detectors, suggested that, unlike the other gas giants, there was not a lot of heat left over from Uranus's formation or any active process inside generating extra warmth. This helped explain why Uranus's cloud features and visible weather looked faint compared to Jupiter or even Neptune, and it brought up new questions about how each giant planet manages or loses its internal energy. Maybe Uranus lost its heat in an ancient collision that flipped it sideways, or its inner structure stalls out the flow of energy. That's still not fully explained, but it's one of the scientific puzzles that came straight from Voyager's flyby. In the details sent back from Voyager 2, scientists also looked carefully at the atmosphere and what was floating around inside. Methane, as mentioned earlier, is what gives Uranus its unique blue-green tint. Voyager's sensors, though, didn't find much in the way of ammonia or hydrogen sulfide clouds that some had hoped for. Instead, the cloud tops mostly contained hydrogen and helium, peppered with thin, high-altitude methane clouds. Because sunlight is so weak at Uranus's distance, more than 2,870,000,000 kilometers from the Sun, clouds don't get the kind of kick solar warmth gives to Jupiter or Saturn. Still, the upper atmosphere was dynamic enough that even with only faint warmth left over, Voyager found hints of cloud bands and faint rings swirling quietly around the tilted world. More than just a flyby, Voyager 2's observations at Uranus gave researchers the details they needed to build the first maps and models for an ice giant. That's the term used for planets with large amounts of ice, water, ammonia, and methane deep in their interiors under thick layers of gas. Before Voyager, models of how planets formed at these huge distances from the Sun were rough guesses. Voyager's direct observations of cloud chemistry, surface features, rings, and the quirky magnetic field gave theorists the first real grounding for what physically happens on planets that never get much sunlight, have a sideways axis, and live out at the edge of solar system dynamics. Of course, the impact of these findings extended far beyond science labs. With crystal-clear photos of rings less than 10 kilometers wide, close-ups of crumpled landscapes on Miranda, and shots of the planet's blue-green glow, the Voyager images lit up classrooms and media all over the world. This was the first time anyone had gotten a face-to-face look at the third largest planet in our solar system. New school textbooks and documentaries from the late 1980s featured Uranus as an active topic, suddenly grounded in rich, real-life detail after centuries of being just another dim point of light. From a mission engineering perspective, pulling off the Uranus flyby wasn't simple. The planet is tilted so far over that pointing Voyager's camera and antenna systems required complex calculations. The rings and known moons were mapped in advance, with help from observations on Earth, but new discoveries made last-minute adjustments necessary. Every minor shift in trajectory risked missing important features, so the mission team worked in near real time, with hours of signal delay to track targets and aim instruments. Voyager's systems performed almost flawlessly, an impressive feat considering most of its parts were already almost a decade old. The discoveries from Voyager 2's Uranus encounter left a long list of follow-up questions. Suddenly, researchers wanted to know whether all ice giants have off-center, chaotic magnetic fields, or if that's unique to Uranus. Did the other planets with rings form the same way? How could a planet like Miranda survive such a violent ancient past and still orbit quietly today? The misaligned magnetic field and sideways spin made Uranus one of the most unique worlds in the solar system, and a kind of test case for ideas about how planets change over time through impacts, cooling, and slow chemical reactions. It's fair to say that a single quick pass by Voyager 2 changed the profile of Uranus from a vague curiosity to a lively subject all its own. Every bit of detailed data, images, temperature readings, magnetic scans, chemical breakdowns of rings and clouds set off a new generation of mission ideas and deeper studies using the best Earth telescopes. To this day, Uranus stands out as a critical, missing piece for space exploration, with its unique position and behavior defining a whole class of planets that we now recognize beyond our own solar system as well. Without Voyager 2's flyby, none of these puzzles or possibilities would be on the table the way they are now. Looking further into the practical outcomes, Uranus taught researchers the value of never assuming the outer solar system is dull or static. The storm scars, extreme seasons, warped rings, fresh moons, and magnetically charged zones mapped by Voyager 2 all pointed toward ongoing change, even without much sunlight. Today, many people in the planetary science community are hoping for a return trip, using modern instruments and possibly even an orbiter or atmospheric probe, precisely because Voyager 2 showed so much happening at Uranus that nobody expected. The legacy of what Voyager saw at Uranus keeps showing up even decades later as astronomers use new space telescopes and ever better observatories on Earth. Ideas about tilted planets, complex rings, and unpredictable magnetic fields pop up anytime scientists study exoplanets that look like Uranus in size and color. There's a whole field now around ice giants that started because for one brief moment in January of 1986, a handful of live photos and blips of radio data from Voyager 2 showed us a tilted, spinning, surprisingly stormy world over 2,800,000,000 kilometers from home. Even though it was just a flyby and not a full orbit or landing, the magnitude of what was gained from this single encounter cannot be understated. The immediate impact on models for the solar system's formation, the deep dives into atmospheric chemistry, the brand new understanding of weirdly shaped magnetic fields, and the revelation of fresh moons and ring features all came from a mission designed on 1970s hardware and a few short, carefully planned weeks of observation. In a very real way, the doors that opened at Uranus are still only partly explored, and the echoes of Voyager 2's discoveries continue to spark curiosity and new science throughout the planetary community, reaching out into our growing knowledge of where to look for the next big find. After the unexpected findings at Uranus, the Voyager 2 spacecraft was set on a trajectory to give scientists their very first up-close encounter with Neptune in the late 1980s. For most people, Neptune had always been a distant, blurry, and mysterious blue planet, its details hidden even from the sharpest telescopes. There just was not much to go on before Voyager arrived. No high-resolution images, no deep atmospheric measurements, and nothing at all about its moons except for bare hints from faint specks of light. As the flyby approached, few could predict just how much Neptune would surprise everyone, not just with its striking appearance, but also with its extreme weather, strange rings, and an active moon orbiting far from the warmth of the sun. Voyager 2 approached Neptune in the summer of 1989, and for several months leading up to the encounter, teams at NASA worked around the clock to update the spacecraft's commands and plan every imaging sequence possible. Even though Neptune receives less than 1,000th of the sunlight that hits Earth, Voyager's cameras managed to capture detailed photos thanks to careful planning and long exposures. The first shock came from the planet's color. Pictures revealed Neptune as a deep, vivid blue, more intense than Uranus, thanks mostly to the presence of methane in its upper atmosphere, which filters out the red wavelengths of sunlight. But it turned out that the real reason for Neptune's richer color could not be chalked up to methane alone. There were likely some unknown components or atmospheric particles enhancing those blue tones. To this day, the exact reason behind that dramatic hue remains a puzzle. The weather at Neptune was next level, even compared to what had been seen at Jupiter or Saturn. Voyager's images and instrument readings quickly showed that Neptune was a world of wild winds and massive storms. Winds near the cloud tops were clocked at over 2,000 kilometers per hour, making them the fastest in the entire solar system. This was an unexpected find. After all, being so far from the Sun, many experts expected Neptune to be sluggish, with only mild atmospheric movement. Instead, the data pointed toward a climate driven by powerful internal heat. Voyager's infrared sensors confirmed that Neptune emits more than twice as much energy as it receives from the Sun, although it is still not fully understood where all that heat comes from or how it keeps driving such dynamic weather. One of Voyager's most important discoveries at Neptune was a massive, dark, swirling storm, later called the Great Dark Spot. This was an obvious, oval-shaped patch in Neptune's cloud tops, roughly the size of Earth. It had strong white cloud features spinning along its edges, and smaller storm systems rapidly formed around it. Unlike Jupiter's ancient Great Red Spot, the Great Dark Spot at Neptune turned out to be highly changeable. It appeared and disappeared over seasons and was gone the next time astronomers got a detailed look with the Hubble Space Telescope just a few years later. The formation and movement of these dark spots, plus extremely bright methane ice clouds, showed that Neptune's atmosphere is far from static. There is an ongoing cycle of storm creation, destruction, and renewal happening all the time. Aside from large-scale systems, Voyager 2 detected atmospheric features at smaller scales too. There were smaller dark spots called Dark Spot 2 and other cyclonic and anticyclonic storms that each lasted for different intervals, sometimes a few months, sometimes longer. Voyager's photos caught narrow bands of clouds racing across Neptune's disk, especially along the planet's equator and at mid-latitudes where wind speeds peaked. These banded storms form and clear up rapidly, suggesting a very active weather layer. All this motion and energy pointed to something strange happening inside the planet. With its rapid supersonic winds and ever-changing spots, Neptune appeared to have an internal heating engine similar in intensity to those at Jupiter and Saturn, although Neptune is smaller and much farther from the Sun. Voyager's measurements hinted that processes deep below the clouds, maybe slow-moving convection or leftover heat from the planet's formation, keep churning up the atmosphere, pushing up visible clouds and feeding new storms. What was most striking is that sunlight alone could not be responsible since the planet receives so little. Even now, exactly how this internal heat is generated or trapped continues to be actively debated. Most people expected to see Neptune's rings, if they existed at all, as faint and thin, not nearly as visible as those at Saturn. Ground-based telescopes had detected possible variations in starlight as Neptune passed by, hinting at arcs rather than complete rings. When Voyager arrived, it confirmed that Neptune does have a system of rings, but it is unlike anything seen before. Instead of broad, continuous bands, Neptune's rings are thin and made mainly of dark, dusty particles. Most interestingly, two main rings, the Adams and Leverrier rings, have so-called arc segments, places where the material clumps together in dense, bright spots. Voyager found that these arcs do not stretch all the way around the planet, unlike the rings at Saturn or Uranus. To this day, scientists are still researching how these arcs stay confined. Gravity from Neptune's small inner moons, especially Galatea and possibly others, may act like shepherds, keeping the ring material bunched up and stopping it from spreading out. That discovery created fresh ways of thinking about how rings behave and what they can look like across the solar system and around planets orbiting other stars. When it comes to Neptune's moons, Voyager 2 made news even before the closest approach by capturing distant blurry images that improved on everything previously seen from ground telescopes. But it was the close encounter with Triton, Neptune's largest moon, that would really stand out as one of the greatest highlights not just of the Neptune flyby, but of the entire Voyager journey. The spacecraft flew nearly 40,000 kilometers above Triton on August 25, 1989, providing humanity the first clear view of this mysterious moon. Voyager's images revealed a surface of pinkish and white tones covered in a complex system of ridges, valleys, and icy plains. There were regions that looked like frozen lakes or seas, scarred by dark streaks and crossing cracks. But the shock came when Voyager's instruments captured active geysers erupting from the surface, spraying nitrogen gas and dark dust several kilometers high into the thin atmosphere. This was the first time active geysers had ever been detected on a world so far from the Sun, immediately changing ideas about what might be happening on cold, icy moons everywhere. Triton's geysers can be explained, at least in part, by a process known as cryovolcanism, essentially volcanoes powered by ice and not molten rock. Energy from the Sun is weak out at Neptune's distance, but even a little can warm some subsurface nitrogen and methane just enough to build pressure and escape through cracks in the surface ice. The dark material from these eruptions settles back onto Triton's frozen crust, forming streaks that can be seen in Voyager's images. This active surface means that Triton is not a completely dead, frozen world, but a truly dynamic place, possibly hiding an ocean or at least a slushy layer under the ice. The geysers also affect Triton's thin atmosphere, feeding it with nitrogen and changing its pressure, density, and temperature season by season. Not only did Voyager 2 discover that Triton was active, but it also found that the Moon's orbit is incredibly unusual. Unlike most major moons in the solar system, which orbit in the same direction as their planets rotate, Triton travels in the opposite direction. This is called a retrograde orbit. Such a path suggests that Triton might originally have been an independent object or dwarf planet captured by Neptune's gravity early in the history of the solar system. This process would have generated titanic tidal forces, which may still be keeping Triton's interior at least partly active. Voyager's flyby gave the first direct measurements of the Moon's temperature, pressure, and ice composition, showing that this oddball moon is one of the coldest known objects measured in the solar system, but one of the most dynamic at the same time. Besides Triton, Voyager 2 discovered and confirmed several other small moons orbiting Neptune, many of which had gone unnoticed from Earth. These moons are dark and irregularly shaped, likely resembling captured asteroids or leftover building blocks from Neptune's youth. Voyager's discoveries forced another rethink about how moons collect, break apart, and migrate around the outer planets, particularly in systems where massive bodies like Neptune might be gobbling up stray objects over billions of years. As a whole, Neptune's magnetic environment was just as confusing and challenging for researchers as what Voyager had found previously at Uranus. Voyager detected a powerful and off-center magnetic field tilted steeply from Neptune's axis of rotation and offset from the planet's center, a feature similar to Uranus but even more pronounced at Neptune. This corkscrewing, lopsided field traps charged particles and creates a magnetic bubble, or magnetosphere, that changes shape as it rotates. As with Uranus, the likely cause is that the field is generated deep inside the planet in thick, slushy, electrically conducting layers of ammonia, water, and methane, not a classic metal core like at Earth. This has major implications for how we think about magnetism on other planets, especially those in our own solar system and beyond. One especially important point about Neptune is that its atmosphere is layered and active, despite very little sunlight. Voyager's infrared sensors mapped temperature and composition gradients from the cloud tops down. The blue color is mainly from high-altitude methane, but Voyager picked out clouds made not only of methane ice but possibly hydrogen sulfide and ammonia in deeper layers. The planet's overall structure is now understood as several broad bands of wind, with complex vortices and rapid changes that can accelerate or stall at different depths. Storms rise and fall through this system, so the planet's appearance always has something new going on. Aside from the raw science, Neptune let Voyager show what kinds of engineering and planning are needed to explore so far from home. Neptune is about 4.5 billion kilometers from the Sun. The light that Voyager captured had to be collected over long periods, and the data trickled back to Earth at an extremely slow rate, with each photo taking hours to arrive. The spacecraft had to time its camera exposures and sequences perfectly because each second of observation counted, especially during the short hours around closest approach. Getting even a single clear shot of Triton's erupting geysers or the rings meant solving countless hardware and timing challenges, but the mission proved up to the task. The flyby had plenty of consequences for what followed in planetary science. Suddenly, Neptune was not longer an afterthought, but a centerpiece in new theories about where planets form, how they trap heat, and how ice and methane drive activity far from the sun. The strangeness of the rings, the power of the winds, and the evidence for a constantly changing weather system forced new ideas about energy balance and meteorology. Meanwhile, the explosion of surprises on Triton, retrograde orbit, geysers, and a complex, possibly young surface instantly made it a top candidate for astrobiology research and future missions. Voyager's legacy at Neptune continues to shape public understanding too. The images of bright blue clouds swirling around the dark spot, the shots of streaks across Triton's pink ice, and even the diagrams of how Neptune's cracked magnetic field works have showed up in classrooms, documentaries, and news stories for decades. They proved that even the solar system's outermost major planet had secrets to reveal on a grand scale and demonstrated the payoffs of sending long-lived spacecraft so far from home. The true scale of what Voyager achieved at Neptune comes into focus when you realize how little was known before it arrived and how much it changed. It answered some big questions like whether Neptune has rings or what is really on Triton's surface. But more than that, it left people with new questions. How do supersonic winds start on a frigid world so far from the sun? What causes storm systems to come and go in just a few years? Could Triton hide a warm interior or even a deep ocean after all? Each answer from the Voyager data made the solar system look richer and stranger. Every new observation and measurement pushed technology to its limits as well. The challenges of sending data across billions of kilometers, keeping sensitive instruments working in the cold and dark, and navigating precisely through a crowded system of rings and moons helped set standards for all missions that followed. The timing, the flexibility, and the tough hardware lessons learned at Neptune supported engineers designing newer probes for even more distant or challenging destinations later on. Researchers today still go back to the Voyager data when working on Neptune and Triton. Telescopes like Hubble and the James Webb Space Telescope have added to the picture, but so much of the core knowledge about the color, storms, winds, magnetic effects, and moon geology comes directly from Voyager's quick but deep flyby in 1989. Modern planetary scientists have pulled information from those first images, the thermal readings, and the radio traces for decades of follow-up studies and mission proposals. Neptune, with its wild weather, mysterious blue glow, and active moon, has grown from a blurry mystery into one of the solar system's most dynamic and compelling worlds. The unpredicted winds, storms, chemistry, and shifting surface features have all set Neptune and its family apart. Proof that the outer reaches of our solar system are full of surprises and not just leftovers waiting in the dark. Triton, especially, keeps pulling new investigators to its case, holding out the lure of more geysers, possibly subsurface oceans, and the story of being a captured object with a strange past. So, as you think about everything Voyager 2 accomplished at Neptune, it is not just what was found that matters, but how it all came together with almost no time for follow-up. A single flyby, one planet, one active moon, and a ring system like no other. It is all in the details, from winds to storms to geysers. The snapshot Voyager left at Neptune is still the only one we have. Every turn of Neptune's deep blue clouds, every flash of light from a frozen geyser on Triton, it all reminds us that even at the extremes of distance and cold, the solar system keeps surprising anyone who takes the time and effort to go and look. After leaving Neptune behind with its wild weather and Triton's icy eruptions, Voyager's mission changed from a planetary grand tour to something entirely new, exploring the vast region beyond the last gas giant, where the solar system's influence finally ebbs away. This phase wasn't part of the original plan, but the longevity and health of both spacecraft opened the door for one more incredible chapter. At this point, Voyager 1 and Voyager 2 each started an extended mission that would take them to the true boundaries of our Sun's reach, well out past all the major planets, into areas where almost nothing was known. Once Neptune was in Voyager 2's rearview mirror, back in late August of 1989, the focus shifted to what's called the interstellar medium. That's the vast, almost empty space between our solar system and the next nearest stars, filled with a thin soup of gas, dust, and charged particles. You hear these words and might imagine complete emptiness, but in reality, there is a border known as the heliosphere, where the constant, invisible wind of particles from the Sun, called the solar wind, meets the wind coming from interstellar space. That border is not a wall, but a gradient where conditions slowly change as you go outward, and until Voyager got close and crossed it, this was mostly theory, not something anyone had measured directly. Voyager 1 shot ahead on a slightly different path than Voyager 2. It was actually the faster of the two and traveled mostly outward, more directly away from the Sun. Over the decades, signals from Earth took longer to reach it as it raced out at a speed of about 17 kilometers per second. Voyager 2, meanwhile, had used its encounters with Uranus and Neptune to pivot southward, ending up angled below the plane of the planets. Both missions, though, had one thing in common. As they drifted further away, they kept collecting unique data with their handful of operational instruments, measuring things that were never even dreamed of when NASA first approved the project. To make this new phase official, NASA started calling it the Voyager Interstellar Mission, basically the last big adventure for these veteran spacecraft. The specific goal was to map the environment outside the influence of the solar wind, catch incoming cosmic rays, and study the transition from our local bubble to the real wilderness of interstellar space. The complexity was almost overwhelming. For example, nobody knew if there would be a sudden, sharp change at the edge of the heliosphere or a gradual fade. Some scientists predicted Voyager would cross a shockwave, others an unexpectedly slow transformation. Either way, the job was to listen and record everything during the months or even years as the spacecraft neared this boundary. On Earth, the way engineers and scientists tracked Voyager's journey was by watching signals transmitted by the spacecraft's instruments. These were slow-moving data streams, sometimes just a tiny trickle of bytes per second, picked up by NASA's worldwide deep space network. The team looked for several key signs: a drop or pickup in the number of charged solar particles, a spike in cosmic rays from the galaxy, or a sudden change in the magnetic field. They also used the plasma wave instrument, the only one of its kind still working on each Voyager, which picked up naturally occurring radio signals or space vibrations caused by changes in the density of interplanetary and interstellar matter. By the early 2000s, Voyager 1 had passed the last major planet and was into the outer heliosphere. This is a zone full of turbulent solar wind that slowly gets less and less dense as you travel farther out. But what Voyager was searching for was the heliopause, the actual edge where the Sun's influence finally stops dominating. The years ticked by. Then, in August of 2012, key data began to pour in. A dramatic jump in the measured density of cosmic rays, a drop in energy from solar material, and new sounds from the plasma detector that pointed to a much denser, more static plasma outside the solar system's border. That was it, evidence that, for the first time, a human-made object had crossed into interstellar space. The measurements Voyager 1 gathered at the heliopause included an impressive checklist. Outside the Sun's magnetic field, the direction and strength of the magnetic environment changed. Cosmic rays, fast particles from supernovae and other galactic events, rose sharply in number and intensity. And, maybe most eerie of all, there were new plasma vibrations coming through, captured and played back as alien space sounds unlike anything measured closer to home. These radio signals are physical proof that the plasma, or superthin gas, is much denser outside the solar wind's bubble. What Voyager experienced and sent back has become the core reference for every study of the real boundary to our solar system, and the first taste of what conditions are like between the stars. Meanwhile, Voyager 2 was lagging behind by several billion kilometers and at a slightly different line through the outer heliosphere. Its path meant it crossed different regions at a different pace. For years, Voyager 2's data painted a second, slightly offset map of the boundary, confirming that the bubble formed by the Sun's winds is uneven, shaped by the Sun's magnetic cycles, and maybe even nudged by powerful events elsewhere in the galaxy. Finally, in November of 2018, Voyager 2 itself logged the same signs as its twin: a rapid uptick in galactic cosmic rays, a sudden change in plasma density, and confirmation that it too had joined its sibling in interstellar space. For scientists, this meant there were now two separate data sets to compare, and, more importantly, proof that at least two regions of the heliosphere could be measured, revealing it is not a perfect sphere but a messy, flexible shell stretching out in all directions. Much of the new science from this interstellar phase comes down to what isn't there as much as what is. Before Voyager crossed the boundary, models of the local interstellar medium had to guess at temperature, density, and magnetic structure. The measurements from both Voyagers now show that outside the heliosphere, the environment is 1,000,000 times thinner than the best laboratory vacuum on Earth, yet still full of slow-moving plasma, dust, and high-speed cosmic rays. These particles are constantly being nudged and shaped, not just by the Sun, but by whatever events have happened over millions of years in our corner of the Milky Way galaxy. The energy seen in cosmic rays is much higher than inside the protective bubble, a reminder that out there, the Sun's shielding effect is gone. The plasma wave detector became one of the mission's most unlikely stars. It worked by recording oscillations caused as charged particles move and collide at the vast boundary. Whenever a new burst of density came in, most often driven by massive solar eruptions called coronal mass ejections, Voyager's antennas would pick up changes in frequency, letting researchers calculate just how thick or thin the plasma was at any given distance. From 2013 onwards, researchers began hearing the plasma sing in a new tone, mapping the first real transition from solar wind to the true galactic environment. The stamina of both spacecraft became newsworthy in itself. By this point, both Voyagers were using radioisotope thermoelectric generators, nuclear batteries that grow weaker every year as their plutonium slowly decays. Scientists had to decide which instruments to keep running and which to shut off for good to save power. Every year, one or two functions were lost, but the most crucial hardware stayed up: the ability to take in particle measurements, monitor the magnetic field, and send slow but steady data back across distances measured in billions of kilometers. Each carefully chosen shutdown was something like an operating room procedure, delicate, deliberate, and a bit emotional for the engineers involved. There was more than just technical magic happening, though. The discoveries made in interstellar space shifted the basic sense of where our planet sits in the larger galaxy. Before Voyager, there was only speculation about how the boundary between solar and interstellar space would work. Now, there was real, physical data. The twin measurements revealed that not only is the heliosphere irregular and bumpy, but that the local bubble of interstellar space may itself be shaped and squashed by the movement of gas, magnetic fields, and big cosmic explosions nearby. For the first time, all those old textbook diagrams of a neat, round solar wind bubble had to be completely updated. All the while, what kept the public's attention were the occasional bursts of news about sounds in interstellar space. These are really rapid rises in plasma frequency caught by Voyager's antenna, then turned into audio waves we can play back on Earth. They sound eerie and strange, nothing like the noises we hear in air, but they are crucial to mapping where Voyager is and what it is moving through. For many people, hearing those recordings, moments of long whistling vibration or strange beeps echoing in the dark, was a reminder that space, for all its emptiness, is never truly silent. Another unexpected bonus came in the way both Voyagers picked up measurements of cosmic rays. Inside the heliosphere, the sun's influence dampens these high-energy particles, but outside, they come in unfiltered. By charting their rise and fall, space scientists have gained better knowledge of how cosmic rays affect spacecraft, electronics, and even astronauts, not just at the edge of the solar system, but also in deep space closer to home or on other long missions. The Voyager twins supply hard numbers for what radiation is like when you are beyond the last outpost of solar protection. The new perspective has also supported missions much closer to the Sun. By comparing measurements from spacecraft like Parker Solar Probe at the inner edge of the heliosphere to what Voyager 1 and 2 are seeing far away, NASA can build a much sharper three-dimensional model of the solar bubble, how it stretches and shrinks with time, and how the Sun's cycle affects conditions at every layer. This is practical science, important not just for curiosity but for designing the next generation of explorers who might one day leave the solar system on purpose, well prepared against what's out there. Staying informed about their health has become a tradition, as Voyager's age means its successes and breakdowns get reported worldwide. With each fading year, transmission power drops, the signal gets harder to find among the cosmic background, and fine-tuning the giant Earth-based dish antennas becomes ever more crucial. Sometimes, a single tiny change in how an antenna is pointed or how an old computer software routine is executed makes all the difference in getting data back. By the late 20s, Voyager 1 and 2 each proved they were not just relics from the past, but working scientific probes operating in a place never visited before. Their ongoing measurements continue to test and refine the boundaries of the Sun's influence. For many in the science world, these missions have turned into time capsules at the very fringe, not just sending home science, but acting as our first physical messengers launched before we really knew what lay at the edges of our home system. The data from interstellar space still trickles down to Earth, sometimes slowly, sometimes with the surprise of a solar shockwave from months before. Every announcement, whether about a change in cosmic rays, a new plasma burst, or confirmation of some structure in the boundary region, makes headlines. The ancient spacecraft, drifting in the darkness, have reached a kind of status as both scientific outposts and symbols of human curiosity. The knowledge that both Voyagers have surpassed their designed lifespans by more than 4 decades adds to their legacy and inspires newer generations of engineers and researchers. For many scientists, the significance of the Voyager interstellar mission goes far beyond charts of particle density and magnetic fields. Voyager's instruments are providing ground truth in a region nobody can yet reach by any other means. Every bit of data about the densities, temperatures, and radiation levels far outside the Sun's protective bubble helps us understand both what shelters Earth and what challenges may lie ahead for whatever travels out next. Each year that the Voyagers survive, they make the case for robust, long-term space hardware capable of weathering decades of unknowns. And beyond the numbers, the mission has changed how we define the borders of the solar system. For decades, there was argument in the astronomy community about where our system really ends. Voyager's journey is proof that natural boundaries are more physical than arbitrary, measured in suddenly changing types of matter, densities, and the presence or absence of the Sun's magnetic signature. This kind of real-world evidence matters not just for charts in science books, but for the next steps taken by future robotic or even crewed missions aiming to leave the solar neighborhood completely. Even knowing how little fuel and power remain, the teams controlling Voyager 1 and 2 keep squeezing out every bit of data. Sometimes this means making hard choices, turning off heaters, putting aging electronics to sleep, and waking up old routines for a last burst of measurements. Each time the team manages to keep an instrument alive just a bit longer, the result is another page of detail added to humanity's map of deep space. As Voyager's journey stretches on, there is a growing sense of what an achievement it is that both spacecraft have ventured farther from the Sun than any object humanity has ever built. The extended mission, the Voyager interstellar mission, may be the most unplanned, unexpected, yet scientifically rich part of the whole adventure. The story now is not just about planets and moons, but about vast boundaries and the constant hum of data coming from the edge, long after the original goals had been passed. Every day that these signal pulses cross billions of kilometers to share news from the darkness beyond the solar wind is a simple, constant reminder that curiosity and a willingness to try still reaches farther than anyone once thought possible. Even as Voyager 1 and Voyager 2 were pushing out beyond the last signs of the Sun's influence, sending back details about plasma waves and cosmic rays, their earlier discoveries inside the solar system were still making waves here on Earth, especially those about the places that could hold liquid water beyond our own planet. It's not an exaggeration to say that the Voyager missions completely changed the conversation around where water and possibly life might be hiding. Back in the 1970s, most people pictured the other planets and moons as cold, dead balls of rock or gas. Voyager's close flybys, though, revealed clues that there might be liquid water under the surface of several moons, places that at first glance looked icy and barren, but at closer examination were hiding much more beneath their crusts. Let's start with Europa, one of Jupiter's largest moons, a place that looked ordinary in small telescopes, but absolutely stunned scientists when Voyager got up close in the late 1970s. What caught everyone's attention about Europa were the long, brownish grooves and lines crisscrossing its ice shell. Instead of seeing a crater-pocked, static world like our own moon, Voyager's cameras revealed a surface that was exceptionally bright, with a maze of fractures and almost no big impact scars. This was puzzling until researchers realized that a world covered in craters is an old one, with a surface that doesn't change much. Europa instead looks almost fresh and active, as if the surface ice is regularly broken, moved, or even melted and frozen again. Digging into these strange lines and grooves, Voyager photos made it clear something had to be happening under the ice. Scientists started comparing crack patterns and measuring the heights and depths of these features using the way sunlight cast shadows. It turned out that many of the ridges are raised, and some have twin parallel lines with a shallow valley in between, almost as if the ice had separated, then pushed back together. This sort of pattern is very difficult to explain if everything is completely cold and still. The simplest explanation is that beneath the shell there's something warmer, maybe a layer of liquid that allows the top to flex, break, and move, acting almost like slow-motion tectonics. The idea of a subsurface ocean went from wild speculation to open discussion thanks to the wealth of Voyager's images. Voyager also measured surface temperatures and looked for any signs of unusual chemistry. Even though Europa's surface is far too cold for liquid water to exist openly, it stays at about -160 degrees Celsius, there were hints that something strange was going on underneath. Researchers found that the surface seemed unusually smooth in places, as if new material regularly oozed out and froze solid. Some areas looked like giant blocks of ice had broken off and floated into new positions, literally rafted across a slushy interior before freezing again. These clues were only visible in high-resolution pictures and were totally unexpected before Voyager's flyby. Europa wasn't the only moon that made scientists rethink what they knew. When Voyager moved on to Saturn, it sent back striking data from Enceladus, one of Saturn's smaller moons. At first, Enceladus didn't seem that special. The 6 largest Saturnian moons had been named for centuries, but Enceladus was often overlooked. But Voyager's cameras snapped images of a world that reflected almost all the sunlight that hit it, making it one of the brightest places anywhere. Large parts of its surface looked smooth and strangely uncratered, even though other areas were heavily battered by impacts. This strange mix of young and old terrain led scientists to ask, could some force be resurfacing Enceladus and erasing its craters? Close examination of Voyager's photos showed systems of cracks and grooves, much like Europa but on a smaller scale. Some regions appeared to be made up of jumbled blocks, and others looked as if fresh material had been squirted out from below. After comparing this new terrain to what had been found on Europa, scientists began to ask if Enceladus too might be harboring a subsurface ocean, or at least pockets of liquid water beneath its crust. Voyager also brought new attention to Ganymede and Callisto, 2 of Jupiter's big moons. These are much larger than Europa, and in Voyager's images they looked a bit more like expected. Lots of craters, some smooth areas, but nothing as dramatic as Europa's clear ice rafts. What was different, though, was the variety seen from one moon to the next. Some features hinted at past flooding or icy flows, while others suggested that even beneath thick layers of rock and ice there could have been, or might even still be, warm spots or slushy pockets capable of holding water temporarily. After the initial rush of excitement around the photos, Voyager's data was pored over using measurements of gravity, magnetic fields, and small shifts in position and orientation. Not all of these readings were as complete as later missions would achieve, since Voyager had only a few hours near each moon and was using technology from the 1970s. Still, the hint was strong enough. These icy moons weren't just dead, frozen lumps. They might have internal heat, supplied not by the sun, but by tidal forces, the constant squeezing and pulling from their parent planet's gravity. For places like Europa, this tidal heating could melt ice below the surface and keep an ocean liquid even in the far reaches of the solar system, where sunlight has almost no warming effect. Voyager's initial findings were so striking that they completely changed what missions scientists prioritized. Instead of just looking for water on planets or big satellites, researchers started thinking about moons as possible homes for oceans and for the chemistry that could come with them. This was a huge change. Before Voyager, the habitable zone was usually imagined as a narrow ring around stars where surface temperature is just right for water to be liquid. Now, with evidence that internal processes could melt ice and make oceans possible far outside that narrow ring, astrobiologists and engineers began planning missions specifically to check for water beneath the surfaces of these unassuming worlds. The Voyager discoveries played a central role in proposals and planning for later missions. Galileo, which orbited Jupiter in the 1990s and early 2000s, used gravity readings, magnetometers, and high-resolution imaging, often following up directly on places first flagged by Voyager as interesting. When Galileo confirmed magnetic evidence for a subsurface ocean at Europa, those results built directly on Voyager's early snapshots and data. Similarly, the Cassini mission, which orbited Saturn starting in 2004, confirmed not just ice but geysers at Enceladus's south pole, plumes of water vapor that erupted into space. Cassini's science team credited the Voyager findings with pointing them to the right moons and types of terrain to investigate further. It's worth pointing out just how powerful even indirect evidence can be in planetary science. Nobody drilled into Europa or Enceladus. Instead, the case for subsurface oceans relies on a web of clues: the way surface cracks appear and heal, the mix of shapes and terrains, the surprising smoothness in certain regions, and even hints from temperature readings. Voyager's instruments spotted spots where the crust seemed thinner or temperatures were a fraction warmer than expected, giving more confidence that there wasn't just cold rock and ice all the way down. One practical outcome of these discoveries is the way they changed engineering plans for getting to and studying these frozen worlds. Scientists started developing radar sounders, ice-penetrating instruments, heat detectors, and cameras that could study faint plumes or complex fractures. Missions like Europa Clipper, scheduled for launch in the 2020s, are equipped with tools that came directly out of the Voyager era's unanswered questions. Even the decision to sample for organics or consider drilling through the ice ties back to those first grainy images of moving blocks and fresh-looking surfaces. Looking at the bigger picture, the presence of hidden oceans opens the door not only to water, but also to the raw chemistry needed for life. On Europa, scientists speculate that the ocean in contact with the rocky mantle below could have churning currents, nutrients, and heat flowing upward. On Enceladus, when Cassini analyzed geyser material, it detected organic molecules, carbon-containing compounds that are the building blocks of life as we know it. Every piece of this puzzle was first glimpsed, at least in part, through Voyager's surprising flybys and the clues hidden in those images. This new focus has also changed how astronomers and planetary scientists prioritize targets in the rest of the solar system and beyond. No longer is Mars the only place with the potential for water-based habitability. Icy moons around Saturn, Jupiter, and maybe even Uranus and Neptune are now viewed as prime real estate for hidden oceans. The idea is that life doesn't just need a warm, sunlit surface. It could survive underground, in salty oceans kept warm by gravitational friction or chemical reactions, and still never see a ray of sunlight. Voyager's contributions continue through all of this. Its legacy isn't just in specific discoveries, but in completely rewiring how we hunt for the ingredients for life. By proving that ice-covered moons can be geologically active, Voyager meant that even ancient distant satellites could be recycling their energy and chemistry through liquid layers. This raises the potential not just for water, but for all the energy and nutrients needed to keep biology running, at least at basic levels. It also forced a new look at the concept of the habitable zone. Instead of a one-size-fits-all model based on distance from a star, the Voyager findings put global oceans on the table as an alternative. astrobiologists started hunting for signs of heat, tidal stretching, or magnetic effects wherever there are big moons closely orbiting giant planets. Exoplanet researchers have even begun searching for similar patterns in other star systems, guessing that icy moons with wild insides could be common. There's a cultural effect, too. By opening people's imaginations to the idea that seemingly dead worlds might hide oceans, Voyager set the stage for science fiction stories, documentaries, and news coverage that treats these moons almost as potential cousins of Earth, not completely alien rocks. That change in thinking has boosted support for future missions, public interest in planetary science, and international collaboration to keep learning more. Looking at what Voyager started, it's clear that a major shift happened in how we choose places for deep exploration. When Cassini spotted those geysers on Enceladus, and when Hubble saw what might be plumes at Europa, the world paid attention in a way that might not have happened if the Voyager data hadn't already painted these moons as possible ocean worlds. Even now, every time a new spacecraft is proposed to visit the outer planets, finding out if there's water beneath the ice is usually close to the top of the science goals. On a practical engineering front, the hunt for hidden oceans also changed some of the most basic protocols about space exploration. Planetary protection became a much bigger concern. If these moons could hold water and, by extension, life, then spacecraft needed to be sterilized more thoroughly, and planning had to ensure that they didn't accidentally crash into and contaminate potential ecosystems. This rethink can be drawn directly back to Voyager's era, since it showed these are places not to be taken lightly. The immediate and long-term effects of Voyager's icy moon findings reach into almost every discipline interested in space. Geologists now interpret fractures and ridges through the lens of moving ice shells or flowing water below. Chemists wonder about the possible soups appearing where ocean meets rock or ice. Biologists speculate about how organisms might survive in absolute darkness, clinging not to sunlight, but to chemical reactions and tidal heat, just as they do near hot vents at the bottom of Earth's own deep seas. Every set of new readings, whether from orbit or a telescope, gets compared back to those first high-resolution pictures from Voyager. The lines, squiggles, and bumpiness drawn on the icy surfaces are still used to guide where new probes are sent or which regions to zoom in on. The questions started by Voyager: how deep is the water? How fresh is the ice? Do plumes really squirt out across the sky? Could anything be living below? Are now the driving forces behind mission after mission. If you consider just how different the science world looked before those Jupiter and Saturn flybys, it's easier to appreciate how many doors were opened by the Voyager missions. Instead of assuming that water and habitability are rare and local, scientists came to realize the solar system might be dotted with more or less hidden habitats, each with unique chemistry and possibilities. The Grand Tour transformed into a survey of where in the solar system might be most welcoming or interesting for life as we don't yet know it. In the end, the discoveries Voyager made about hidden oceans beneath icy moons did not just boost curiosity. They forced a shift in the actual science and the strategies of explorers. With every new proposal, every line of code sent to a robotic lander, and every conference meeting where scientists debate where to drill, echo after echo of those first Voyager glimpses show up. The hunt now extends not just around our sun, but out to other stars, searching for worlds with that special combination of water, chemistry, and hidden warmth, forever changed by what two spacecraft found drifting past worlds where nobody thought water could survive at all. As Voyager's discoveries about hidden oceans and active worlds under thick ice changed what scientists looked for in the solar system, there was something else on board both spacecraft that spoke on a very different level. Traveling along with the sensors, cameras, and computers, each Voyager spacecraft carried a metal disc, the Golden Record. This was not just a technical add-on or a tool for measurements. It was meant as a gesture, a message, something like a calling card from Earth, meant not just for us, but for anyone or anything that might find the spacecraft one day in the deep future. The story behind the Golden Record goes back to the mid-1970s, before the launch of Voyager 1 and Voyager 2. The team at NASA, led by astronomer Carl Sagan and including artists, engineers, and linguists, started to think seriously about what kind of message, if any, humanity might want to send into deep space. They had a practical reason for this. Voyager's path meant each craft would leave the sun's orbit forever, possibly drifting among the stars for millions or even billions of years. Since both Voyager spacecraft would eventually stop communicating back home, the idea was to give them a small chance to speak for us long after we were gone. Choosing what would go on the Golden Record was a once-in-a-lifetime assignment. The record itself is a gold-plated copper disc with instructions etched into the metal so that, in theory, a technologically advanced being could figure out how to play it. Each record is protected inside an aluminum cover and comes with a cartridge and needle, similar to what old vinyl records use, showing how the grooves should be read to hear the sound. Along with the hardware, little line drawings explain the basics of where the spacecraft came from using maps of known pulsars, so the finder can figure out Voyager's origin in space and time. Selecting the content for the record was tough. The project team had just a few weeks to assemble everything: pictures, sounds, music, and greetings, because the records had to be finished before the spacecraft were shipped to the launch site in Florida. The main goal was to represent the diversity of life and culture on Earth, but in a way that would have meaning even after translation across huge cosmic distances and unknown cultures. In the end, the Golden Record included 116 images, a collection of sounds from nature and daily life, a handful of pieces of music from around the world, and greetings in 55 different languages, both ancient and modern. A lot of thinking went into which images and sounds to use. They picked photos of everyday life, city traffic, families eating, men and women working, along with pictures of animals, plants, and landscapes. Some images are highly technical, like diagrams of human anatomy or mathematical equations to show a potential finder how carbon atoms are organized. Others are much simpler, like a mother with her child or people laughing and eating. The aim was to paint a picture of both the science and warmth of human life. Sounds included thunder, wind, ocean surf, rain, the singing of birds, and even a kiss. The musical selection mixed famous Western composers like Johann Sebastian Bach and Ludwig van Beethoven, with folk music and more obscure tracks, such as a wedding song from Peru or a traditional Japanese melody played on a bamboo flute. In the original spirit of balance, the team made sure to include works from all inhabited continents, hoping to show the range and flavor of our planet. There were practical obstacles too. Some musicians and record companies refused permission at the last minute, so choices had to be changed rapidly. The greetings were a particularly creative solution. In a world where no one could know who or what would ever find Voyager, the team went for inclusion. Short hello messages from all over the world, recorded in dozens of spoken languages. There's also a message from then United Nations Secretary-General Kurt Waldheim and a printed statement from Jimmy Carter, who was President of the United States at the time. "We are attempting to survive our time so we may live into yours." These messages were simple, warm, and sometimes awkward. but the idea was to offer the hope of goodwill, if not a guarantee of understanding. One of the clever details about the record is the inclusion of the sounds of Earth. This is an audio collage, almost like a radio play, that lasts a few minutes and layers the noises of the planet into a tapestry. There's a train, a horse running, a heartbeat, laughter, footfalls, and more. The sounds move from the natural, wind, surf, thunder, to the human, tools, engines, and the launching of a Saturn V rocket. For a finder who knows nothing about Earth's technology or biology, it's a little slice of what being here sounds like. There's also what might be the most universal attempt at a message. Hour-long recordings of what's called brainwaves, simple electrical signals generated as a woman named Anne Druyan thought about life, love, and the fate of humanity while attached to a sensor array. Modern listeners might think it's an abstract touch, but the team wanted to include something uniquely human, even if its meaning turned out to be impossible to decipher. Physically, the golden record is designed to last. Unlike paper or tape, the copper and gold construction survives radiation and cosmic dust much longer. NASA calculated that unless Voyager crashes into something big or wanders into a star, the records could outlast the spacecraft and, in the cold vacuum of deep space, remain readable for at least hundreds of millions of years. The metal case even includes a diagram showing how to play the record and calibrate the speed using a vibration mode linked to the fundamental properties of hydrogen atoms, an attempt to ensure a universal frame of reference. From a technical process standpoint, the team had to invent ways to transfer photographs and sounds to grooves in a physical record. This meant transforming everything into analog waveforms that could be physically etched. Even as digital technology was beginning to catch on in the 1970s, Voyager's message stuck to tried-and-true mechanical formats because nobody could be sure what a potential finder would have, and vinyl-style grooves are pretty basic physics. There's an important difference between the golden record and earlier messages sent out by other spacecraft. The Pioneer plaques, a set of small engraved messages attached to Pioneer 10 and Pioneer 11 earlier in the decade, were simple diagrams with a man, a woman, and basic solar system directions. The golden record, by contrast, tried to cover not just what we look like, but how we live, what we hear, what we find beautiful, and how we communicate. In terms of sheer data and detail, it's far beyond anything previously sent into space. The public attention around the golden record was huge, both at launch and in the years since. Magazine articles, TV specials, and news programs have revisited its content many times, and there have even been reissues of the sounds and images for people to buy and listen to at home. Even people who do not follow space news closely have heard jokes or references to "Hello from Earth" traveling beyond the planets. The golden disk has inspired songs, books, and films, and has spurred debates about what should represent humanity in case of a real encounter. The project was not without controversy and criticism, both then and now. There were arguments over what music got included, whether certain images, like photos of naked humans or maps of our home system, might be dangerous, and whether it was wise to send a message without knowing who might receive it. There were even suggestions to encrypt or code the content, but the team decided openness and honesty were the best path given the context. Throughout, the creativity and good intentions of the golden record's makers were clear, and the process emphasized speed and practicality just as much as philosophy. For NASA and for the Voyager science team, the golden record is not the official purpose of the mission, but it is one of the most enduring public contributions. Space science usually deals in numbers and data, but the record made many people feel directly invested in the mission. When footage of Voyager crossing Neptune or reaching interstellar space aired alongside snippets of the record's content, Even non-scientists were moved to feel included in a much wider story. There is also the reality that the odds of Voyager ever being intercepted are extremely small. Space is unbelievably vast, and both spacecraft are moving through regions that may never come close to a star or planet for millions or even billions of years. But the point was not certainty, it was possibility. Every time a probe leaves the solar system, people now think seriously about what messages it might carry, who we are speaking to, and whether it is right or wise to send greetings into the dark. Voyager set the standard, and its golden record is the yardstick for outreach projects, whether real or just imagined for future missions. One surprising effect is how the project united scientists, artists, and ordinary people from all backgrounds. The process involved translators, musicians, researchers, writers, and many more people, each making choices and suggestions. Every Voyager launch anniversary, the golden record pops up in articles, exhibits, and educational programs. It is now part of the permanent collection at the Smithsonian and other space museums, and in 2017, a complete replica won a Grammy Award nomination for Best Boxed or Special Limited Edition Package, a small but telling sign of its cultural footprint. For the new generation growing up after the Voyagers were launched, the golden record stands as a weird but powerful introduction to what space exploration can mean beyond just science returns. Students and artists alike look at the record and ask what they might send if it were up to them. What would they choose from their own lives, cultures, and favorite music? That curiosity leads to projects in classrooms, art studios, even global debates about representation and science diplomacy. NASA has learned valuable lessons from the golden record. When designing later missions bound to leave the Sun's orbit, there is often some consideration given to a message or time capsule, no matter how simple. The act of choosing a greeting, a photo, or a melody is now always paired with hands-on engineering challenges and scientific calculations. It is a constant reminder that exploration, even in outer space, is as much about humanity's self-reflection as it is about distant discoveries. Other spacecraft, such as the New Horizons probe launched in 2006 to Pluto and beyond, have carried onboard messages, but none as ambitious or comprehensive as Voyager's record. Even outside NASA, international missions take their cues from Voyager. The practice of including a cultural, diplomatic, or artistic artifact is far more common now, with the golden record almost always cited as the reference point. Looking at all this, what one piece of technology has given more than decades of news stories? The simple golden disk, barely larger than a dinner plate, has done something the rest of Voyager's data cannot do alone. It has bridged science and the wider cultural imagination, inspiring hopes, questions, and a sense of global belonging. Every time humanity thinks about stepping out into the cosmos, the memory of the golden record is there, not just as a memento, but as a challenge to rethink who we are and what it means to reach out beyond our own world. The fact that these records may outlast civilization as we know it is not lost on anyone involved. In a practical sense, the disks are more like cosmic bottle messages, unlikely ever to be picked up, but still worth sending. The act of choosing what to share, whether it is a photograph of schoolchildren, a greeting in Zulu, or a Baroque fugue, has become part of the Voyager myth. The legacy is ongoing, even as the original team has aged or passed on, because every new generation can discover the contents, listen, and imagine. So, as the Voyager spacecraft keep moving silently further into interstellar darkness, the golden record travels with them. It carries a collection of Earth sounds and scenes that will likely outlive the computers, cameras, and sensors that made Voyager famous for data. The record is a living time capsule, a scientific artifact, and a cultural symbol all wrapped together. Its journey does not require listeners or interpretation to have meaning. It was and is both a scientific effort and a personal gift, an offering launched into the cosmic ocean, quietly inviting any finder in any future to know that for a moment in time, a small blue planet tried to say hello. And while the golden record turned the Voyager spacecraft into something like time capsules and cultural ambassadors, the core of their impact actually rests on something less glamorous, but even more impressive: the story of their engineering, adaptation, and survival across all these decades. Most people do not realize just how much ingenuity and hands-on crisis management went into keeping both Voyager 1 and Voyager 2 running since their launches in the year 1977. From the moment each spacecraft left the launch pad, their teams have had to tackle a mess of technical risks, design challenges, and unexpected failures, and do it all with technology that was beginning to age long before either probe even crossed the orbit of Jupiter. It started in the planning phase, when NASA engineers faced the problem of building machines meant to handle situations no one could perfectly predict. The probes would need to fly past 4 wildly different planets, then try to keep working as they left the solar system entirely. The power source chosen was a trio of radioisotope thermoelectric generators for each Voyager. These are nuclear batteries that take heat from the natural decay of plutonium and turn it directly into electricity. Back when they were first turned on, each generator could produce a little more than 470 watts of power, more than enough to run all instruments, cameras, and heaters. But the design team knew that every year the power would drop, and after a couple of decades, the teams would have to start making hard choices about which instruments should stay on and which needed to be switched off for good. One of the first major challenges hit only days after launch, when mission controllers had to confirm that the dozens of mechanical and digital systems survived the shaking and vibrations of takeoff. The computers on board the Voyagers were not like modern ones. By today's standards, they're primitive, using only memory measured in kilobytes and relying mostly on hardware switches and basic logic chips rather than software running on fast microprocessors. This limitation turned out to be an unlikely advantage. Fewer moving parts and simple logic meant there was less to go wrong, and what issues did arise could sometimes be fixed from millions of kilometers away by sending new instructions encoded in radio signals. During the early flybys, problems came fast. A tape recorder used to carefully store images from Jupiter and beam them back over the limited data link jammed up temporarily, risking the loss of precious photos. The team on Earth spent hours practicing with backups, running mock recovery steps, and then sent a set of unpredictable, sometimes risky instructions that finally got it working again, all while the signal bounced back and forth over hundreds of millions of kilometers. At Saturn, sunlight was too weak for effective solar cells, and temperatures had dropped so low that some parts of the spacecraft risked freezing up. The engineers had built in small electric heaters to keep mechanical arms and computers warm, and devised a rotation maneuver so that the vulnerable face of the probe would heat up whenever conditions got too risky. Crisis management became a routine rather than an exception. There were moments when gyroscopes needed to keep the high-gain antenna pointed at Earth drifted out of calibration. With no people in space to nudge things, controllers relied on tiny releases of compressed gas in the attitude thrusters. The fuel for these thrusters was limited from the start, so each correction, sometimes measured as little as 1/1000th of a degree, had to be carefully tracked. The engineering staff would exchange calculations overnight, practicing on simulators at NASA's Jet Propulsion Laboratory, and then transmit final commands hours in advance, hoping to see the right result on the next day's downlink. After making it through the smoke and radiation belts at Jupiter, Voyager's engineering team learned something everyone else would benefit from for decades. The environment around Jupiter is so hazardous, with radiation levels high enough to fry exposed electronics in just a few hours, that many circuits and chip surfaces had to be shielded. Over the years, new space missions to Jupiter, like Galileo and Juno, all relied on the lessons and hardware tests derived directly from the rescue efforts and band-aid solutions pulled off by Voyager's technical crews. Once both spacecraft started heading for Saturn and farther, another kind of engineering challenge appeared. The decreasing amount of electricity from those nuclear batteries forced mission controllers to make choices. Which instruments mattered most? Should the heaters go off, knowing the risk of letting cryogenic temperatures freeze the fuel lines or damage sensors permanently? Every couple of years, specialists would meet and decide which scientific experiments could be powered and which needed to go dark. So the main transmitter, the memory banks, and the navigation gear would have enough energy to function. It was never a completely downward trend. Sometimes, new discoveries meant creative use of old hardware. One famous example came when the planetary radio astronomy experiment, left on mainly as a backup after Saturn, picked up strange plasma waves just as Voyager was leaving the heliosphere. With the main imagers long since powered down to conserve electricity, the team programmed radio and particle detectors to run new routines, storing data over weeks and then sending it back during short phone-home windows when the planets in the way would not block the signal. Software also played a much bigger role than originally intended. In the year 1977, rewriting code from Earth was untested and risky. By the late 1980s, mission managers had become experts at sending highly compressed or entirely new tables of instructions, often using a spare memory bank as a test bed before making any changes to the live operating software. Sometimes this meant holding back images for days until the patch could be uploaded and confirmed. Stories circulated inside NASA about near misses, like when a fault in the error detection algorithm caused commands to be garbled and sent the crafts into safe mode, requiring days of careful troubleshooting to wake the instruments back up. Physical redundancy was crucial too. Both spacecraft were designed with backups for almost every important piece of gear: a spare transmitter, extra gyros, secondary heaters, and so forth. When a tape deck failed or thrusters clogged, the controllers could swap to a spare circuit or change the pointing strategy, often on very short notice. The reality for the team on Earth was a mix of celebration and stress. Every backup system used was one less safety net for the decades remaining. Communication has been an ongoing challenge, growing harder every year. When Voyager left Earth, its signal strength was more than enough for NASA's big dish antennas. But every million kilometers further out, the radio drops off by the square of the distance. By the time Voyager approached the edge of the solar system, the signal was thousands of times weaker than at launch, bouncing around at a fraction of a nanowatt, about the same as the energy from a single small LED Christmas light. NASA's Deep Space Network had to upgrade its receivers, improve data compression techniques, and even pool more antennas together in a technique called arraying, just to catch the faint beeps and packets. Weather on Earth could cause delays or loss of data, so every viable downlink had to be carefully scheduled and protected. Real-world events have taken their toll. In the 1980s and 90s, NASA's budget went through periods of tightening and threats of cancellation. When Voyager moved beyond Uranus and into truly unexplored zones, the case for additional funding was made every year by showing just how much new science still emerged from these elderly probes. Much of the flexibility and dedication in the ground teams, constantly shrinking as workers retired or projects wound down, came from the mission's proven resilience and ongoing stream of discoveries. A lean, cross-trained group of controllers, often with decades of experience on the same craft, was built up to handle multiple emergency scenarios at once. Hardware on both spacecraft has also aged in unexpected ways. Some paints and adhesives used on outside parts turned brittle after decades of radiation exposure. The wires carrying commands and science data would sometimes experience small shorts or changes in conductivity due to temperature swings with each orbit around the Sun. Antennas warped ever so slightly, and protective covers over the nuclear batteries began to show signs of cosmic ray bombardment. Whenever a new problem came up, NASA's team had to act almost as much as mechanics as they were scientists, testing components in cold chambers back on Earth and trying out new ways to nurse systems along just a bit longer. Onboard memory, measured in kilobytes rather than gigabytes, has meant that storing and prioritizing data is an art form. The science team reviews every bit of data received, sometimes arguing over which readings really matter and which can be skipped in the interest of saving bytes. When a glitch causes data loss, there is no way to resend. What is gone is lost forever, so storage, transmission, and backup are all managed with a level of focus that you rarely see in modern spaceflight. When new discoveries from the spacecraft, say a plasma burst or interstellar radio sound, are made, the team quickly assesses how much of the spacecraft's health can be risked to grab the data. There have been cases when the engineers paused safe heating cycles or allowed minor system voltage to drift risky more than planned, all to keep the probe alive just long enough to catch something scientifically unique. This delicate balance between scientific ambition and hardware lifespans is a regular part of mission management. The accomplishments amid all these hurdles span more than the hardware, too. A big part of Voyager's technical success is the almost constant stream of training, documentation, and knowledge transfer among the team, engineers and scientists alike. As the years have rolled on, the original mission crew handed their knowledge over to new generations, sometimes through handwritten notebooks or hours of late-night troubleshooting calls. Every conservation technique, every creative software patch, and every strange system quirk has been recorded and referenced, ensuring that no bit of hard-won expertise goes untapped if trouble hits again. There have also been institutional challenges, shifting priorities, transitions between NASA management teams, and even periods where the agency debated simply turning off the spacecraft to save costs. Time after time, the case was made that keeping Voyager alive was not just about prestige, but about real engineering value. Museums, schools, and other missions around the world would gain from whatever the spacecraft learned about toughness, resourcefulness, and efficiency. The lessons from Voyager's engineering have shaped everything that came afterward. Missions like Galileo, Cassini to Saturn, and even the New Horizons probe to Pluto all borrowed techniques for problem-solving, redundancy, error correction in code, and communicating across astronomical distances. Today, deep space missions almost always include multiple contingency plans, more spare components than are strictly needed, and the capacity to rewrite and patch software even years after launch. Not only did Voyager outlast the planned 4 years, but it's also set a standard for spacecraft endurance everywhere. At each stage, Jupiter, Saturn, Uranus, Neptune, and finally into interstellar space, the engineering bar has been raised higher. What was once just a bet that the probes would last through flybys of the first 2 planets turned into a multi-decade endurance test. The fact that both spacecraft are still sending back data more than 40 years after launch is a testament to layers of smart choices, careful design, and inventive, real-time fixes in the face of unexpected problems. When NASA marks each Voyager anniversary or key milestone, the celebration often centers less on where the probes are and more on how long they have survived and how much has been learned about operating in deep space. It's rare in the history of technology to see such old machines still performing useful work, adapting to aging parts and reduced resources. The technical accomplishment has become a point of pride not just for the United States, but for the global community of space engineers and fanatics everywhere. Every maneuver, software tweak, and crisis has told a bigger story. That deep space exploration is not about flawless design alone. It is also about keeping your cool when the guidance system glitches, stretching a few kilobytes of memory to cover one more priceless measurement, or cross-training a skeleton crew to troubleshoot what nobody could predict decades ago. For all the focus on science and discovery, Voyager's technical legacy is as much about flexibility, persistence, and the determination to wring as much as possible from every ancient wire and sensor still working out beyond the edge of the solar wind. Decade after decade, even as systems have grown dim and transmitters have faded, the ongoing operation of both spacecraft underscores what long-term spaceflight is all about, balancing innovation, risk, resource management, and adaptation against a background of harsh, unforgiving conditions. There are always fresh problems ahead, but every new lesson from Voyager has sent ripples through the world of spacecraft design and mission control. The journey of keeping both probes alive is, in itself, as remarkable as the discoveries they've sent back, and continues to define what it means to go the distance in space exploration. The story of how Voyager lasted through countless technical risks, emergencies, and decades of distance does not end with the survival of two plucky spacecraft. Its biggest impact is how those missions changed not only science but also world culture and our plans for the future. Even now, more than 40 years since their launches in the year 1977, the reach of Voyager goes much further than the signals still being picked up by giant radio dishes. The payoff is bigger than a list of discoveries. What we take forward is a whole new idea about our place in the universe and a practical roadmap for those who want to push beyond our solar system. Back when Voyager was first imagined, most textbooks painted the planets as faraway dots. People knew some rough facts about the outer solar system, but the continents of those worlds were blank. Looking at Jupiter, Saturn, Uranus, and Neptune was a matter of blurry telescopic images and the occasional hint from a passing probe. After Voyager's flybys, books, maps, and models had to be completely redrawn. The missions sent back thousands of images, radio data, and temperature readings that defined a new age in planetary science. The Great Red Spot, the volcanic eruptions on Io, the colors of Neptune, the structure of Saturn's rings, and the possibility of hidden oceans under ice. This was no longer theory or guesswork, but concrete observation collected and shared. Scientists now describe the data sets from the Voyager missions as gold mines, still not completely exhausted after all this time. Researchers are always finding something new to tease out because the information covers so much ground. Weather on the planets, chemistry of exotic atmospheres, measurements of magnetic fields, the discovery of rings, and the layouts of moons nobody ever imagined. In classroom after classroom, the story of Voyager moves students from memorizing names to actually seeing and thinking about new worlds. Weather patterns on Jupiter, for example, are now taught as dynamic and changing, not just painted swirls. Books on astrobiology always cite those first strange images of Europa's cracked surface and Enceladus's smooth, bright regions. This redefined the zone where life might be possible and turned those moons into targets for future exploration. But what often gets missed is how much Voyager's results set up every deep space mission that came after. Galileo, Cassini, and even the New Horizons flyby of Pluto built their entire mission plans around findings made by the twin Voyagers. When Galileo was sent to Jupiter in the 1990s, its engineers studied the radiation readings and hardware troubles Voyager encountered in the planet's fierce magnetic field. The Cassini probe to Saturn, launched in the late 1990s, picked its targets for detailed study because Voyager showed which moons and rings were most interesting. Even the Europa Clipper mission that is headed for launch in the 2020s is shaped by old Voyager flybys and their hint of oceans under the ice. Scientists use Voyager's measurements as their before snapshot. If something looks new or different today, it keeps raising good questions. In practical terms, the long life and reliability of Voyager forced the world's space engineers to expect more from their hardware. It showed that a smart mix of tough construction, redundant systems, and clever software can keep a mission running far beyond what anyone dares to promise at the start. Planners now build in more backup systems, emphasize reprogrammable computers and remote upgrades, and take more care with crisis training for mission control teams. Modern scientists and engineers expect to encounter new problems after launch, and the learning curve from Voyager is still being used for missions like the Parker Solar Probe and James Webb Space Telescope, showing that old-fashioned toughness and adaptability still beat the odds. Voyager's lessons about planetary systems keep spreading farther, especially as astronomers discover planets beyond the Sun. When scientists look at giant exoplanets circling other stars, they now see hints of storms, rings, strange clouds, or hidden heating, phenomena first documented close up by Voyager's flybys. Data from our own gas and ice giants are often the only reliable touchstone for guessing what an exoplanet's environment might be like. Even the discovery of worlds with sideways spins or lopsided magnetic fields is easier to understand because Uranus and Neptune taught those lessons first. The data from Voyager still guides mission proposals and target selection for billions of dollars in research spending. Long before a new spacecraft is designed, teams pore over old photos and readings, picking out puzzles to solve or regions to revisit. When a camera or sensor finally captures something new, experts line it up against Voyager's benchmarks to sort out real change from random noise. In this way, Voyager's output is constantly refreshed. It anchors science that is always evolving and connecting forward and backward at the same time. Culturally speaking, Voyager turned public attention to deep space in a way that almost nothing else had before. News about the flybys, especially in the late 1970s and 80s, made headlines and sparked imaginations globally. The first images from Jupiter's storms, Saturn's icy moons, and Neptune's blue clouds appeared in magazines, television, and even postage stamps. Documentaries and novels spun the story into classrooms and living rooms. For millions, the idea that a machine built on Earth could reach out that far long after its creators retired changed how space was discussed with families, in schools, and in the media. The Golden Record itself became an icon, inspiring other outreach efforts, science fiction, and even art projects. People from every country have seen or heard the story of the record's "Hello from Earth," and the idea continues to pop up in pop culture references, movies, and novels. There are bands, exhibitions, and projects built around what humanity would say to the unknown, a direct echo of the Voyager project's influence. Back in the science world, Voyager's discoveries continue to prompt new questions about habitability. Now telescopes and future missions chase after any world with evidence of water, liquid, ice, or vapor. Planetary protection rules have tightened up. Now every mission to an ocean world needs to sterilize itself more, all because Voyager made it clear those places could hold signs of life. When Galileo showed strong evidence for an ocean under Europa's ice, and Cassini flew through geysers at Enceladus, the initial clues were traced back to Voyager's first snapshots and rough measurements. The habitable zone for life keeps getting moved wider and wider. The practical lessons from Voyager also run deep in spacecraft operations. Every long-lived mission now emphasizes multiple layers of fail-safes, creative uses of old or backup tools, and teams ready to improvise. When the New Horizons probe ran into a glitch on approach to Pluto, NASA's confidence to diagnose and restart the mission came straight from the hands-on lessons learned in the Voyager years. Continued teamwork, training, and careful documentation all echo what worked during old Voyager crises, making sure every unexpected blip is met with clear thinking and fast action. Endurance is another key part of Voyager's cultural tailwind. Few other space projects last long enough to outlive their designers, but with Voyager, whole generations have watched the same two probes keep ticking off new milestones, crossing the orbit of another planet, leaving the heliosphere, or releasing new space sounds as they meet interstellar plasma. These updates keep Voyager relevant and familiar to people decades after launch. There is also a shared sense of pride among engineers and scientists, not just in America but worldwide, for what Voyager represents. Teams from around the globe have reused and learned from its open data archives, and the public records are now referenced by students, professors, and mission planners everywhere. The idea that it is possible to reach out and explore so far, survive so long, and keep returning value year after year is a signal to every space program about what is truly achievable with determination and engineering discipline. On the educational side, Voyager footage and photos continue to turn up in science lessons. Whether it's explaining gravity assists and slingshot maneuvers, or showing how cameras can find volcanoes, storms, and ice flows in places where nobody expected active geology. Space camps, university labs, and even school science fairs often reach for Voyager as a touchstone, using its story to explain why we keep going back to the drawing board, updating old ideas with each new batch of data. In a more strategic sense, Voyager's example has made future exploration more ambitious. The success of a multi-planet tour with decades-long survival gave NASA and other space agencies the confidence to plan for missions like Cassini, Juno, and even attempts at interstellar probes that may one day follow the Voyagers out. National and global policies for deep space exploration often cite Voyager's technical legacy and its ability to keep the public interested as a key reason for funding future adventures. Beyond science and strategy, Voyager has sparked fresh cultural ways of feeling about our place in the universe. For many, just knowing that a human-made object is still out there, drifting further from the sun every day, carrying a hello from Earth, invites a kind of curiosity and humility. It is not about conquering space or finding quick rewards, but about steadily learning new things, sending home messages, and building up our map of what's possible bit by bit. At a policy level, the Voyager journey has pushed for open data and collaboration. The vast trove of images, spectra, and radio readings has been public from the start, available to research groups, universities, and amateur astronomers everywhere. This spirit of openness helped promote new global standards for sharing discoveries from NASA missions and has shaped how agencies across the globe handle their planetary science output. Looking ahead, the roadmap Voyager created is still driving big choices. The Europa Clipper, Dragonfly to Titan, and Mars sample return missions all have roots in Voyager's discoveries and the tools it inspired. Future plans for probes that could visit the edge of the heliosphere, and even dreams of robotic or crewed interstellar missions, are built on the foundation of the paths first blazed by Voyager 1 and Voyager 2. Even now, every time a deep space photo gets shared or a science breakout session makes headlines, it pays a little tribute to Voyager. Spacecraft being prepared for launch in the 2020s and beyond look back to the past for their software design and hardware safety tricks. Engineers and scientists alike talk openly about the need for endurance, remote crisis skills, and public outreach. 3 things Voyager showed could turn a science project into a cultural legend. And of course, the spirit of optimism and adventure that marked the Voyager launch in the year 1977 has not faded. For those planning the next round of missions, the lesson is clear. Aim farther, double-check your gear, and remember to build in some poetry and imagination for good measure. Whether you are calculating gravity assists or deciding what song to record for the next golden disc, the expectations set by Voyager are always in the background. Where does this leave us now? Voyager's ongoing journey, still sending home signals at the edge of the sun's bubble, acts as a persistent reminder that persistent effort adds up over time. No single discovery sums up its impact. It is the full mosaic of better science, smarter spacecraft, new mission types, expanded ideas about life, and a deeper sense of connection across countries and generations. As new explorers prepare to leave Earth, with slingshot hopes and better mathematics, the story of Voyager rides ahead, showing what's possible with careful planning, creative fixes, and a readiness to learn with every new mile. So each time the faint pulse of Voyager's signal reaches home, it is not just an echo of a past technology. It's a living link to the day humanity first set out to see just how much there is to discover out past the last planets, the last rings, the last sunlit places we knew. The legacy is not just the pictures or the science returns. It is the changed mindset, the rolling curiosity, and the perpetual motion that define humanity's perspective on the cosmos from here on out.